that last little device we used.
Yeah, because we want to be able to have DC coupled all the way through. And so we want the midpoint to be a ground potential there. If we don't use a bipolar supply, then we have to use coupling capacitors so we can have the voltage swing plus and minus.
I see. Coupled. When you say coupled,
That means you're allowing the signal to pass without screwing up the DC voltages.
right. Right. Okay.
So the capacitors pass AC, not DC. Where's
I'll let him know.
oh, yeah. Kevin's sick today, so he's watching from home.
Dang. Not to rush you, but to rush you. Oh, Kevin's sick today?
Yeah,
Okay.
he's watching from home. So.
Oh, good. Sorry. That's no, that's a lot of stuff. I know. I hear you.
How's your weekend?
Oh, busy.
Yeah. Okay, well, any questions from what we covered so far? Anything at all?
Oh, man. Remind me again, a lot of times we're next to a capacitor, we're using a resistor. Remind me again why do we have to do that? Why are we doing that? Is it because it's DC?
Well, what circuit? What example are you specifically?
Well, with the, as we're building a, what should we call it, in the transistor circuit.
Yeah, well, we use coupling capacitors on the input and output because what that does is allows us to pass the signal without upsetting the DC voltages. Remember what we had to do to get the bias right?
Right.
And we want our signal to not affect that at all. So we want to pass the AC from the signal, which is what we want to amplify, without messing up the DC voltages.
Okay. And
So
why are we using a resistor there usually?
Well, where? In what part of the circuit?
Right next to the, well, not all the capacitors actually, but usually have a resistor near there.
Well, it depends on what the circuit is. I mean,
Right.
the op amp itself is, you have two resistors there. You have the feedback resistor, which determines the total,
Yeah.
the ratio of the feedback resistor and the input resistor.
It's very specific on each one. Okay, yeah, I just appreciate that. That's it.
Okay, well, this is going to be different here. Since the general focus of the GROL class has to do with the radio technology, so we're going to, from here on out, going to be talking a lot about radio. We're going to pull everything else that we learned up to this point here. Now, one thing that makes radio technology different is so far we have talked about lump components, which are basically components that are in a specific location. We have a resistor here, we have an inductor here, we have a capacitor there. When we start working with antennas, we no longer have that. We can no longer isolate them into individual components, but we have what we call distributed components. So we have a piece of wire, for example, would have a distributed number, an infinite number of infinitesimal inductors in series. So we can no longer say this is an inductor here. What it is, we've stretched this inductor out over a long distance. Same with capacitance. The capacitance is distributed over a long distance, and then any resistance we have will be also distributed as well. Most of the time, the resistance that we're using in antennas is going to be this mysterious entity called radiation resistance, which we're going to describe in great detail here, because that's going to be important to almost everything we do from here on out. But let's see. I'm using this fluorescent stuff. The only one that shows up is that guy there.
The orange.
to get myself some black pens, I think. Like, can you guys see that okay?
Oh, yeah, we can see.
Yeah, the camera just doesn't do justice. But anyway, there's a couple of definitions we'll talk about. First of all, when we're talking about electromagnetic radiation, we are talking about everything between subaudible electric fields up to cosmic rays. So we have a huge radio spectrum of electromagnetic radiation, and the commonality of electromagnetic radiation is the fact that it does not need a medium to transfer. Unlike sound, where we need to have air in order to transmit sound, in electromagnetism you do not need a medium. And several famous experiments, the Michelson-Morley ether drag experiment, which basically showed that we don't really have this thing called ether, which had been assumed to be a medium through which light travels for hundreds of years. So it actually didn't disprove that the existence of ether, but it proved that ether was not necessary. So, very interesting history on there, but
Yeah.
you ought to read up on the Michelson-Morley
What was his
ether
name?
drag. Michelson-Morley, a couple of English experimenters. I've read their first names, the hyphenated last name, two guys that basically did a lot of experimentation to show that the speed of light was constant regardless of whether you're moving toward the source or away from it, which is really kind of a bizarre thought when you think of it. But they also... So anyway, electromagnetism is all the same in the fact that you have a magnetic field and a electric field at right angles. It doesn't matter whether this visible light, which is a small chunk of the entire electromagnetic spectrum, or ultra low frequencies or whatever. You still have these two fields, and that's what allows it to propagate without having a medium. So now we did demonstrate pure magnetic induction by having two coils next to each other, and the magnetic field collapsing and expanding and intersecting the other coil. But that's not an electromagnetic radiation because, first of all, it's confined to a very small area, and it doesn't propagate through space, other than, unless you happen to actually be in the magnetic field. Whereas true electromagnetic propagation is not confined to any physical object there, so it will propagate through space forever and ever. And so, how do we generate electromagnetic wave? Well, the simplest way to generate electromagnetic wave on the very smallest molecular level or atomic level is anytime you have a moving charge, or I should say an accelerating charge, it's going to generate an electromagnetic wave. So if you take an electron and accelerate it, it's going to create an electromagnetic wave. And same with a proton. However, a proton, as we mentioned, is 2,000 times as massive as an electron, so it takes a whole lot more energy to get a proton accelerating. So most of what we're working with in order to generate electromagnetic waves is going to be squirting electrons back and forth, sloshing electrons back and forth. So to take things well, let's talk about some definitions here. What do we mean by wavelength? Well, one thing that's constant in everything we do is the speed of light. The speed of electromagnetic radiation, regardless of the frequency, is going to be the speed of light, which is very close to 300 million meters per second. It's not exact, but it's very, very close. And it's a lot easier to remember than the speed of light in miles per hour, or miles per second is 186,292 miles per second. So it comes out a much rounder number if we use the metric. Now, as much as I despise the metric system for most things, for electromagnetics, it's always been metric. Radio's always been measured in wavelengths and meters. So it's one of a few applications where it's actually more convenient than almost anything else. But it seems to be going that way. But I'm glad we're still in the English system for the most part. So anyway, when we talk about wavelength, what we're talking about is we have an oscillating electric and magnetic field, and it is one complete oscillation. The distance it travels is one complete oscillation. Now, we talked about before when we were talking about sine waves and frequency, where the frequency was determined by not so much its physical movement, but the alternating polarity of it. In this case, we actually are talking about the physical movement. So when we talk about antennas, we can have, for example, when we talk about the phase shift, we aren't talking so much about the phase shift in terms of time, we're talking about phase shift in terms of space, where different things happen. So an antenna you can have, unlike and this is where you'll have to kind of modify your thinking. You remember in a series circuit that the current's always going to be the same everywhere. That's not true in an antenna. We have an antenna which has a current which changes depending on where you are on the antenna. So a lot of those rules there, they aren't violated, but we have a whole different set of hardware that we're working with. So keep that in mind. That's one of the main differences that we will find about distributed components as opposed to fixed components is the fact that not everything happens at the same time. So you have to say, well, what's happening here may not be the same as what's happening here. So in terms of wavelength here, we have this formula here, just like everything else we have. We have a nice little magic circle that we can do, and it's because almost anything we do in science is you have one component which is a product or some specification in terms of some other. So little c is the speed of light that we use, and as opposed to big C, which is capacitance. So we want to make sure that we don't keep our case sensitive. Little lambda here actually has capital lambda, which is the symbol for wavelength.
Okay.
And then we have frequency. So the unit of wavelength is, we're going to be using meters for the most part. Sometimes we get real low frequency kilometers, or we work up to light frequencies, we use angstroms.
Wow.
But for the most part, we'll use our unit of wavelength is going to be in meters. And frequency again is in hertz, and C is a constant with speed of light, so C really is its own unit. We don't have C measured in any unit, so keep that in mind. It's kind of like the number pi, there's no units of pi. Pi is the fundamental constant. So
we don't say meters per second, but
no.
It is.
Here we will. Now, when we talk about the actual, meters, yeah, that we can use that, but keep in mind that we can always go to your fundamental units if you get confused here. So, so it's going to be rather than saying meters per second, we'll say C is distance per time. I guess that's the best way to express it. So it's going to be a little more useful there. So so it's 300 millimeters per second. So that'll as we start working with actual physical antennas, you might want to use kilometers or micrometers or centimeters. In amateur radio, we go to higher frequency UHF bands. We talk about centimeter wavelengths, that sort of thing. Now, one of the fundamental things that we want to know about any antenna, the fundamental, most basic antenna, is going to be a half wavelength long. This is our fundamental building block for any antenna we have. So it has one oscillation or half an oscillation of current along the distribution. Now, with these in mind here, let's talk about a little more about the fundamental dipole antenna. And the dipole system means two poles. In the vacuum tube, we get a diode, which is two electrodes. In the antenna, we have two poles. So let's just take extremely simple situation here. So if we take a piece of wire and break it in the middle, and we put a generator right here, and make an AC generator, okay? And we apply some AC voltage at that point. How much current's going to flow?
Well, it seems like none.
No, okay, that's good first guess. Because it's not a complete circuit. At least in DC it's not.
Right.
But as we increase the frequency, we find out that we have a delay time between the current and the voltage getting into there. And the delay, again, is not always in time, but we can express it in terms of position. If we imagine like a U-shaped channel of pipe here with some water in it, and we have a pump down here at the bottom, and we slosh it one way, well, until power's gone from one side, we can keep pumping current into it, and then it goes away, and then we can reverse a polarity. So what we're doing is we're sloshing, there's a little oversimplification, but we're sloshing the electrons to one side, during 1/2 cycle, and then the other. Now, as we mentioned before, it's not the electrons that are actually moving the whole distance, it's the actual energy, so we really want, the electrons don't move very far.
Right.
But the energy does here. Now, if we cut this antenna to exactly half wavelength at whatever frequency you're using, you can pick any arbitrary frequency. Let's take 7 megahertz. It's in your lower frequency amateur bands. So 7 megahertz. What's the wavelength of 7 megahertz going by in this formula?
Well, we should do the calculation here.
Yeah. So go ahead and do a calculation. We know what C is, right? Write that down. And F is going to be 7 million.
Right.
First one to come to the answer gets a brownie button.
7 million.
Yeah. 7 million hertz.
Let's see.
Okay, and what units?
Meters.
Yeah, okay, so 42 meters.
Ah.
That's full wavelength. That's a full wavelength antenna. So
Full wavelength.
Full wavelength, but we don't use full wavelength. We always use half wavelength. So we're going to cut ourselves a piece of wire which is 21 meters long. Okay. Now, when we do that, and we run a generator at the middle there at 7 megahertz, we will have a current distribution that looks like this. Now, it's obvious why it would go to 0 at the ends, because there's nowhere for it to go. Okay, you have the electrons sloshing back to the middle. Let's say this point, at the midpoint, we have the most water flow here. Everything from here, this point on, has to go through that point. But the farther away you get from the pump there, the less has to travel through that point. So every electron we slosh through here has to pass through the midpoint, but as we get closer to the end there, we have progressively less current flowing at this point.
Mm-hmm.
Now, we also have something else happening, and in order to get the current to flow, we have to create a voltage. So what we have is a voltage distribution looks like this. So at this one end of this antenna is going to be maximum polarity, maximum voltage one polarity. Here is going to be maximum voltage of the other polarity.
Okay, always, or they switch?
Well, that swaps every cycle.
Okay.
So this is going to wobble up and down like this, and the voltage is going to reverse itself like this.
Okay, and the first one that goes up like that, what is that?
That's current.
Current, okay, current.
And I always have my nice linky here to demonstrate that. Okay, so there's a half wavelength.
That's right.
That's half wavelength between. So as a musician, you should be very familiar with that. Okay, so that's a half wavelength resonating. Pulling at the ends mean it can't move because there's nowhere for it to go. So the end is going to be fixed in terms of current. So we have no current flowing at the ends. We do have opposite voltage flowing at the ends here.
Yes.
So we have a generator here. We have current flowing, and we have voltage across it. Now, what do we know about circuits that have no resistance in them? How much energy is used up?
Should be none.
Should be none, okay? We don't have any resistors in here, do we?
Not technically, no.
Okay.
Wire.
Okay, well, let's say we have a perfect wire with no measurable DC resistance in it.
I would say no.
Okay. So, what are we doing?
Right.
What's the point here, right here?
Yeah.
Well, we have this mysterious entity called radiation resistance.
Yeah.
And it's nothing you can measure with a ohm meter. We can measure it with a grid circuit. So, we have in free space, we have no other objects around, a half wavelength dipole, and again, this is at any frequency as long as it's a half wavelength, whatever frequency you pick. This mysterious R sub R, radiation resistance, at the feed point in the middle is going to be 72 ohms. That's in free space. Once we have reflections off the ground or whatever, it's going to change, but 72 ohms is your radiation resistance in free space.
No matter what the wavelength.
Regardless of what the wavelength of the frequency is for a dipole, half-wave dipole antenna.
So it's RR?
R sub R.
R sub R.
Now, what, if we were to measure the voltage and the current at this point, that would be a real power loss.
At that point.
At that point,
Yeah.
it's real power. How do we know it's real power? Well, because if we have a generator, we're going to drop voltage and current, and they're going to be actually in phase here as long as this is resonant. If we're too high or too low a frequency, then the phase, there's going to be a phase shift. But as long as this is resonant at the feed point at any point, the voltage and current are going to be in phase. Now, what's really interesting about this is we won't measure any heat here. But what we do is radiate into space. Okay? So this radiation resistance can be calculated just as if it's a real resistance. We can measure the current and the voltage and multiply them together here. And put the voltage across here. Multiply those together, and lo and behold, it's going to be a real power. And we're going to actually radiate that power. And that's the actual power that does work for us by radiating a signal into space. Which is the whole idea of an antenna in the first place, right?
Yes.
But number to remember now, when we get antennas in logical heights, it generally tends to lower the impedance here. The reason so much of your radio frequency equipment is designed for 50 ohms is because antennas in most practical environments are usually quite a bit lower than 72 ohms in free space. But we can,
that's in free space.
That's in free space. Any questions?
A lot, like why, but yeah, I'm sure we'll get into it. Then I'm assuming that, the ground and other objects around, everything is affecting how much can be radiated out.
Yeah, you get reflections and absorption and but it's, we always start with the ideal, so in free space is what.
Yeah.
Now, would that be like, I deal in satellite, which is.
Yeah, well, you have a lot.
Yeah,
this is the most fundamental antenna you get. When you get the VHF and UHF, you start using many more reflecting elements. And
so we had an issue in one of the villages I worked in, actually just yesterday, where there was a tree that bent down in front of the dish.
Oh yeah, well, that will definitely.
So it would have changed that.
The microwave frequencies.
Oh yeah. Yeah.
Would have changed that 72 to something
higher.
higher.
Could it be? It depends on
Okay.
the little chart that shows whether it's going to increase or decrease.
Increase for you, really?
Yeah. We assume everything in free space for this point here. Now, let's go back to our magic slinky here. We have the current distribution across the antenna, which is very important to decide what's happening. But then we also want to know what's the radiation pattern look like? Where does that radiate the most? What direction is that? Where does it radiate? Put a generator there. Where's the maximum radiation going to be, and where's the minimum going to be?
Assume the maximum would be
Well, let's
In
say a
which
set
direction?
for a given distance, okay?
Well,
Which direction is that gonna radiate the most?
straight up and down probably the most. I
Well,
would assume.
this is in 3 dimensions, okay?
Oh, 3 dimensions?
What's it gonna look like in 3 dimensions?
I mean, oh man, I'm making assumptions here, but
Yep, that's good.
like, oh man, I don't know. Is this working?
That's working.
I'd say something like that, kind of like that, and the same up here.
Okay, it's close. It's,
Good guess?
what's gonna look like is your little bagel with a point converging in the middle, okay?
Oh.
So that's the radiation pattern of a dipole. And, the important thing is,
Sure.
one of the important things is there's absolutely no radiation in the line of the antenna itself. There's
Right.
Absolutely nothing out this way.
Nothing.
Perfect, no.
Wow.
So that's your fundamental dipole radiation pattern, and we work from there to modify it to get directional antennas and that sort of thing. Now, because it's radiating in a whole bunch of different directions, right? We have to say, well, this is going to be the most direction is the broadside to the antenna.
You can't
Yeah.
say that.
You can say that. Now, as we get to longer antennas that are not resonant, we'll show what happens there.
Right.
Now, a radio signal, we know that attenuates as it goes from distance, okay? Now, we talked about like decaying sine waves where you have resistance in the circuit and it goes away and eventually. A radio signal in free space where you don't have any absorptive items, okay, in free outer space where there's nothing to use up any energy there, it's still going to attenuate, and that's called geometric attenuation.
Wow.
Because what you're doing is, because this thing is not a laser beam, okay, you're shooting all the rays parallel to each other out here.
Uh-huh.
As you get a certain distance away, you
Oh,
get what's
right.
called a spherical wavefront. So basically, it looks like an expanding balloon.
Mhm.
And the surface area increases as the square of the distance. And if we consider the total radiated power equal to the surface area at any point from there, we find out that the power dissipates as a square of the distance, regardless of how strong it starts with, or the original power, because of the fact that unless you're a fully collimated laser beam where every ray
Right.
is parallel to each other,
Right.
it's always going to attenuate, but it's what we call
Right.
geometric attenuation. So we, because I have a good analogy of almost any antenna, you take a beanbag chair, which has the same surface area, and you can punch a bunch of different shapes and reorient the direction of the signal, but it's always going to the total radius signal is going to be proportional to the surface area of the beanbag chair. You got a certain amount of leather out there today. But it's always going to attenuate with distance. So the farther we get away, we're going to have an attenuation. And that's with no losses whatsoever. So when we talk about the attenuation, that's
And
a
light
signal.
does the same thing, right?
Light, yeah,
acts the
exactly,
same
yeah,
way.
yeah.
Okay.
Whereas laser beam, the perfect collimated will not attenuate. It'll be the same distance
Right.
of a million miles out as well at the point there.
But then you'd have to be at the exact point where that's pointed
That's
in
right.
order to
That's
measure
right.
it. If
That's
you're
right.
off,
That's right.
you wouldn't see it?
That's right.
Yeah, okay.
Okay, so we start out with even your what we call normal age radio frequencies between like maybe AM broadcast band up to maybe 100 megahertz or so.
Okay.
Most of our antennas are not going to be very directional. They're going to be pretty non-directional there. Now, if we want to, let's talk about a few variations of this. Yeah, well, I guess the inverse square law is probably the big one. If you measure the voltage at any point in time, it's going to attenuate as a square of the distance. And you notice that inverse square law happens to everything. The RC time constant, so it's always some sort of logarithmic curve with attenuate, which is nice because if it worked that way, we wouldn't still be receiving signals from Voyager 1, which is 30 billion miles out in space. With a certain distance, it does die. It just,
Right.
but it attenuates, but never gets to nothing.
Right.
So that's our fundamental transmitting antenna. And we need to talk about another important concept called reciprocity.
Reciprocity.
Reciprocity. Now, it kind of goes without saying, but I always have to say everything that goes without saying because there's always somebody who's
Right.
it's not obvious
For
to.
news.
Well, we would assume that if our purpose in transmitting a radio wave is for somebody to receive it someplace, right? Not too much point in transmitting without some intended audience, right? So we have to receive this radio signal that we so wonderfully radiated out into space. So how do we do that? Well, we use an antenna, which has exactly the same characteristics as a transmit antenna.
Ah,
Now, I'm drawing just a vertical antenna just for a couple of simplify a few things here. So we mentioned how do we radiate a signal? How do we create an electromagnetic wave to start with?
AC current.
Yeah, but what's actually radiating? What's causing the radiation?
Electromagnetic.
So that's what's before that. What's the fundamental cause of electromagnetic radiation?
Is that with the AC current, with the voltage going up? Well, let's see.
Even more fundamental than that.
Even before that, huh?
Movement of electrons.
Accelerating movement of electrons.
Oh, well, there you go.
So we have generated this radio signal somewhere out there
Uh-huh.
by accelerated electron, and we'll assume we're accelerated up and down. Of course, out in space, there's no definition of up and down, but assume we have some reference point. So now we have a electromagnetic wave that's coming in from somewhere, and this is oscillating up and down, and we have a wavelength of some sort, you know. And then what happens is the electric part of that wave, as it intercepts the atoms in the antenna, it's going to cause electrons to accelerate up and down in the antenna.
Mm-hmm.
So now this antenna looks like a generator to anything beyond that point.
Wow.
Okay. Now here's a great analogy. Well, how can a receiving antenna being a generator? Okay. So let's go back 200 years here. So we have a sawmill run by a stream outside, and there's a paddle wheel outside, and it's cranking the shaft there, and you've got a sawmill or a grain grinder inside, and you're the guy running the sawmill, and you've never been outside your little cabin. So all you know is there's a shaft coming in from somewhere, and the shaft you can extract power from and use it to run your sawmill or whatever. So is a shaft the generator of power?
No.
Where's the power coming from? Out there, okay?
Right.
So you're extracting a very small percentage of what's going on the stream. You got a mill stream out there, and you've got a little
Right.
paddle wheel in there that's sucking off a teeny tiny amount. Now, it's really efficient, maybe like a hydro dam, you can
Right.
extract most of it. But this paddle wheel, you don't know anything about what's out there, okay? It's just a flow of water, okay? And you're sucking a little bit of it off, but as far as you're concerned, it's the shaft that's got the power. Well, same thing here. You've got this electromagnetic field out there, and you're extracting just a minuscule portion of what's out there. I mean, that could be just if you look at a radiated signal 1,000 miles away, and the amount of energy you absorb over the whole thing is, just trillions of what's actually being made. So you're using a minuscule amount of power that you're absorbing from this stuff going by.
Wow.
So, from the point of view of anything here, the source is right there. Like the antenna is absorbing that electrostatic energy from the field, accelerating electrons up and down here. When you have electrons being accelerated, you have a generator. So now we can replace that with a generator here, and that can be used to power anything downstream, or you can have something that we can work with radiation resistance of a receiving dipole is exactly the same as the radiation resistance of a transmitting. The radiation pattern is exactly the same. So our standard bagel-shaped pattern doesn't matter with transmitting or receiving. So that's what we talk about when we talk about reciprocity. It's the pattern. No one doesn't care whether it's transmitting or receiving. It's kind of a very interesting and very useful concept. So, two antennas very close to each other, and they can also have magnetic coupling, and we talk about high gain antennas to do that. But generally, when we talk about this reciprocity thing, we assume the antennas are far enough apart that they have no direct interaction with each other.
Okay.
And that's what we call the far field behavior. As we start moving two conductors closer together, you start getting the magnetic coupling, just like you would with two coils there.
Right.
And that's your near field behavior, which is a little bit different. So
Because both have electrons moving inside them, so it's going to start.
they don't get radiated.
Yeah.
I know that, I don't remember a ton from my Army days, but I know when I was setting up retrans sites, we were supposed to keep the antennas a certain distance apart. Is that they'll?
Yeah, well, you're running two different frequencies there. Yeah, you're running two different frequencies. You don't want to interfere with it. They've got feedback, which is not what you want. So.
Yeah. And I've also heard for like CB radio, like for going up the haul road, you don't want two antennas too close either for that.
Well, you don't want too close to something else, and if you're using it as a phaser array, then you can. But you can. It's not just the receivers themselves are going to get a little lower than one frequency, so it depends on the selectivity of the actual receiving equipment. Now there's a thing called a passive repeater that's, there used to be some up and down pipelines, where you just had basically a parabolic dish here, a piece of transmission line, and another parabolic dish here. And it was just for getting over hills and stuff where you just didn't, it wasn't convenient.
Sure.
Yeah, I said, you don't have to power it. It's just passive, totally passive.
Wow.
And because of the reciprocity, we know it's going to work. Any signal coming in here is going to be absorbed by that, transmitted down the transmission line. There's a lot of loss in here. It's not a real efficient thing, but sometimes all you need to do is get over a hump someplace, you know.
And what are the components of that again?
Two parabolic antennas
Parabolic.
and a piece of transmission line in between.
Yep.
Now there's trillions of different types of antennas now, but traditionally there were basically considered two fundamental types of antennas. One was a Hertz antenna, which is the half wavelength dipole that we talked about. And then we have the Marconi antenna, which is a quarter wavelength, and it works across a ground. So assume this is an infinite conducting ground surface, like if the earth were paved with copper. Now underneath their broadcast stations, it usually is pretty much paved with copper. You have 120 radials of copper wire underneath every tower there. It goes out a quarter wavelength, yeah. So there's a lot of copper under broadcasting.
Stuff like that?
Down on the Mexican border for years and years and years, they've had a hard time keeping the copper there because the Mexicans would come across the border that I don't know how they ever knew this stuff was there. Just a few inches under there. They come there and pull all the ground screens out, and the transmitters wouldn't work anymore, so they go back and lay it all down again, you know. So, I mean, copper's a little bit valuable, but not enough to risk your life there. Because somebody's with a shotgun going to take you out if he's pulling their antenna apart, you know. So anyway, the Marconi antenna is a quarter wavelength long, and then the other half of the antenna is this ground radial.
Oh, wow.
So we can actually replace it just for safety argument with two radials here. And the radiation resistance of a Marconi antenna is half of the dipole, so it's 36 ohms. Now, it used to be when AM broadcasting was king and everybody was involved in radio at all was involved in AM broadcasting. This was all stuff that was all knew like the back of their hand there, but now this is becoming lost information here. But this is the kind of just very fundamental to what we did in broadcasting. So, typical quarter wavelength vertical antenna for us. Usually been
Quarter wavelength.
quarter wavelength, yeah. Oh. So that's your typical Marconi. Now, since radio towers come in 20-foot sections, nobody saws an antenna to exact resonance. You know, they take the nearest, 20-foot section they have, and if you come out anywhere near a resonant frequency, you're doing pretty good. But we'll talk about matching antennas later on, how to compensate for it. But basically, fundamental, this is going to be the same. It's going to have the same donut radiation pattern. Looking from the top, there's no radiation going straight up. So if you fly over, you ever done any flying where they use ADF receivers or ADF transceivers for direction finding, and you fly directly over the AM broadcast tower, it's gone. There's a kind of cone of silence overhead. So, but the whole point of AM broadcasting is transmitting very strong signals at ground levels.
Mm-hmm. Well, and you were going to say the broadcast dimension of it looks like what?
Oh,
On one of
it
these?
looks like
It does look
like this, like that, except vertical. Yeah.
Oh, yeah. Gotcha. And so with that copper mesh on the ground, I'm assuming that's reflecting?
Yeah, it's actually the other half of the antenna.
The other half of the antenna.
Yeah.
Oh, I see. Oh.
Okay, so little thought experiments.
Mm-hmm.
Here's a full wave antenna. What would the radiation pattern look like at that? Now this has other problems besides that.
Full, yeah. Well, I mean, if it's full length, wouldn't there be an issue with the dipole being at the middle, or not?
Well, the feed point is definitely be different here,
Okay.
because when we're feeding it, where the current is maximum, the impedance is going to be very low. That's going to be minimum, which is 72 ohms. This is going to be several thousand ohms at the feed point. So,
Whoa.
first of all, the feed point is going to be all squirrely.
Right.
Now, it doesn't mean we don't use it. It doesn't mean it's a bad antenna. It's just that everything's going to be changed here. Another thing is, what we have is two dipole radiation patterns, right? It's like two standard dipoles next to each other.
Right.
Except, one of these is fed 180 degrees out of phase with the other one.
Right.
When you take all those signals together and combine them together, you have something, the radiation pattern looks like this.
Really?
Yeah. So if that's your dipole, you no longer have maximum radiation perpendicular to the antenna. You actually have a null perpendicular to the antenna.
Yeah. Uh-huh. Okay. There's some. Does that strengthen the signal in those other areas, or is
It does, yes.
does?
You do get gain.
You do get
Now, if we want a lot of gain, we just make the antenna really long. And that's what the oldest antennas are. This is called a couple ways of doing it. Let's do say the antenna 5 or 6 wavelengths long. We just keep adding wavelengths on. What we're going to eventually going to end up is some lobes that are going to lie very close to the line of the antenna.
Uh-huh.
They're also going to have all these little side lobes too. The more wavelengths you have in there, you're going to have your main lobes, your side lobes. That's nothing you can get away from now. That may or may not be a problem. We'll talk about very high precision antennas where, like with radar, where you can't tolerate that kind of stuff. But for general communication, that's usually not a problem. We have pretty good high gain here, but it's not exactly in line with the wire. So what you can do here is we can put 4 of these together. And what we can do is we can adjust these angles here. This, let's say each of these is 4 wavelengths long. So each one would have a radiation pattern look like this. And let's do the same thing out here. So you see these, if we align this right, these ones here and these are going to be in a straight line, so they're going to reinforce each other.
They reinforce.
And same thing down here.
Uh-huh.
To align them, we have to adjust this angle here, and we have to adjust the actual wavelength. But this is called a rhombic antenna, and it was the most high gain possible antenna for point-to-point communications. They used to actually use these for between here and the lower 48. The military had a lot of rhombics sitting down there. There's still some remnants of some of them. Usually not built these on telephone poles in England. So very, very old, very reliable antenna. As a matter of fact, AT&T, when they had some of the first telephone companies that actually used radio for interlinks, used rhombic antennas for that. So there's theoretically no limit to the gain you can get on these, as long as you don't have a limitation of real estate. You just keep making longer and longer, and you got more gain, you know.
Wow. Theoretically.
Well, in real, I mean, you actually, back on what's the name of that? Something said Long Island where RCA did them, and they had a 40-mile long.
Oh, wow. Oh, the blasting.
Yeah, I mean, until Long Island was, they covered one end of Long Island to the other, and said, well, I can't go anymore, you know.
Wow.
And they kept
40
that.
mile long
40 mile.
antenna.
That's a very strong signal.
Yeah, the early days RCA, very narrow, very strong. Do what you have to do what you're doing.
Yeah.
We're really low frequencies, you know.
And then, okay, wow. What was that called again?
That's a rhombic.
Rhombic.
And there's 2 ways you can give the half rhombic. One is called an obtuse V, and one is called a V-beam. So you can actually get rid of this half.
Okay.
Or you can get rid of the bottom half. So if you didn't have either a height for a tower or whatever, you know. So there are all sorts of variations of that. So they all fall in the category of what's called long wire antennas. And then one final class of antennas is actually 2 subclasses, but loop antennas, like this guy here. Okay. There's large loop antennas and small loop antennas. The small loop antennas are usually used for direction finding.
Like that. Direction.
Direction finding, yeah. You want to know where a signal is coming from. Loop antenna like that has a radiation pattern, which is actually null. Yeah, let's see. Have to get oriented. Very clear. I guess I should mention one other thing. We'll go into too much radio propagation now, but in general, low frequencies, such as the AM broadcast, are vertically polarized, and they actually travel in contact with the surface of the Earth. So, the Earth is, the propagation velocity through dirt is a little bit slower than it is in free space. And so if you have a wave that's propagating partially underground and on top, what's going to happen is the wave that's underground is going to want to go a little bit slower than what's on top, so it's always going to want to bend toward the Earth, which is a good thing, which is how you can get over long beyond the horizon propagation on radio. So it actually clings to the surface of the Earth there. So that's called true ground wave propagation. And this is what most of your AM broadcasting relies on for anything beyond a few miles. So. And so it's vertically polarized, which means the electric field is going to be vertical, or if you're rate generating from an AM antenna, it's going to be the same. The polarization is always going to be the same direction as the wire you have. Now, there are pure magnetic antennas where the polarization is not defined by the actually or physical orientation of the wire, but for almost anything we're going to be working with, if the wire is vertical, the polarization is vertical. So that's going to be the electric field here.
Okay.
Vertical polarized antennas, vertical polarized waves are the only ones that will travel in contact with the conductor like the Earth. If it's horizontal, it'll just short out. So you cannot get ground wave propagation with horizontal polarization.
It'll short out.
It'll short out.
Interesting. Huh. Ground propagation. And that's for certain wavelengths, you said, like
Lower frequency, yeah. Get up to high frequency like VHF, the loss to the Earth is so tremendous anyway, you don't normally use it. So yeah, you spend all your energy heating earthworms up.
Yeah.
But anyway, if we're looking for this is a vertically polarized small loop, and we want to find out which direction and receiver transmitter is relative to that. We rotate that for a null, and what it turns out, if we have a small loop like this looking at the edge, we're going to have a perfect null off the sides of here. So we're going to have this radiation pattern coming out this way, we're going to get nothing.
Okay.
So we rotate that to the front side and we say, oh, the radio signal goes away, and that's where there's the signal coming from. So this is what's used in all your automatic direction finding on aircraft. So you use a beacon, say
where the signal goes away, you're saying, oh,
yeah, where a signal goes away is where, because you can, it will start looking in the high gain antennas, will find out that it's always easier to get a very sharp null than it is to get a very narrow beam.
And so what you're showing us right there is if that antenna up there was turned, like facing us?
Yeah.
Not facing us, but...
Well, edgewise, yeah.
Oh, okay. That's where the null is.
Yeah.
Okay.
Now, there's what's one disadvantage of this in direction finding?
Left to right.
Yeah, you could be 180 degrees off, okay?
You could, yeah.
So really what's that, unless you have a good idea about where it is, you can say, well, yeah, we know it. So somewhere out there, then it's okay. If you don't have any idea where it is to start with, then you modify this pattern to get what's called a cardioid pattern, which is half of this. So you generate a cardioid pattern, and then you know this null here is going to be at this side. However, a cardioid is never going to be a sharp null. So you make it a temporary cardioid pattern, so you can find out within 180 degrees where you want to be. And then you switch back to your normal pattern, and then you just narrow in on that. The antenna...
Make a cardioid pattern of what?
Of the actual radiation pattern. What you do is it's called a sense antenna. What you do is you put another vertical polarized antenna near it.
Okay.
You mix the two signals together, and that alters the radiation diagram there. So.
And I'll get your point in the right direction.
Yeah. So you get yourself in the ball within 180 degrees, and then you get the one thing.
I bet that's something they'll have AI doing pretty soon.
Well, they got some I got some pretty sophisticated antenna modeling stuff right here. I can show you some of that. So, you know, we talked about the fundamental antenna. Everything's use that for the basis for any kind of high gain antenna you want. You work with satellites a lot and use parabolic dishes, right? So, generally have at the focal point here, we have a dipole of some sort. Sometimes that'll be actually aiming toward the antenna. Lots of variation. But if we just have a dipole up here, that has radiation pattern, which would be the donut shaped thing, and anything that's radiated this way is going to be reflected off. And you get a semi-collimated beam out there. Get the shape right. Which is one. Not as much radiation patterns out there.
Right.
Now, obviously, since the dipole already radiates a certain amount of energy in this direction as well, that can either work for you or against you. If that happens to be out of phase with what we have there, then it can actually work against you. So generally, yeah. So most of your high gain communications antennas actually have another subreflector here.
Interesting.
And that's to make sure that the direct radiation up here isn't screwed. Yeah.
Kind of like the Bose cancellation headset.
Well,
out of phase, it'll actually.
Oh yeah. Well, all that acoustic stuff is identical principles for
Wow.
RF.
Wow. Okay.
So this is generally called a subreflector there, and this is usually parabolic, and this is usually hyperbola. There's other shapes there that come up. Now, for a given amount of real estate, usually parabolic antenna probably has the most possible amount of gain. However, for very long frequencies, it's not too practical. So we don't start using parabolic antennas until we start getting up to the microwave region. Okay, so let's talk about somewhat simpler antennas, but they're based on. Let's look down on an antenna. Okay, so here's a dipole. We know the radiation pattern is in the dipole, right? Looking from the top and taking a slice out is just going to be a circle, right? And we're going to have the same thing here.
Another dipole. Okay.
So if we space these things and we use quarter wavelength spacing between them. Play around with all sorts of things. So quarter wavelength spacing between these, and we radiate them. So what we have these radiated waves that go like this, and like this, and where they overlap there, they reinforce. So if you look at where they reinforce, we're going to have the reinforcement of both these in this direction. So we're going to have a kind of a squished out dipole pattern like that.
Okay. Yeah.
If we feed these 180 degrees out of phase,
right. So what we're looking at is, what are we looking at? Just an antenna?
just at the end of it, dipole.
Okay, yeah, that's right. Oh.
We're fed 180 degrees out of phase,
Oh, yeah.
and that's also two colors. Red is your positive. Positive link, and there's you have here. And if we look at where the troughs and the valleys overlap here,
right,
we find out there's going to be a null. So we're going to have a null in this direction. We're going to have more radiation out the sides, and then a null in the middle.
That's if they're 180 degrees out of phase.
Yeah.
Because they're, again, like canceling each
Yeah,
other.
just kind of like two waves canceling each other.
Right.
Yeah.
Okay. Okay.
And one of the very popular antennas, and we mentioned the cardioid there, which is used for direction finding, but also has some other uses there. Use cardioid mics to get rid of sound coming from the back, right? There's one right there. This one, No, right here. That mic,
Oh.
there's a
Oh, right.
hypercardiolate. So if we put these quarterly length apart, and we feed them 90 degrees out of phase, we end up with
Huh.
a perfect cardioid, with a perfect null in this direction, a little bit of reinforcement out that side. It's got a cardioid that looks like a bird.
Wow.
So these are your two classes of antennas is phased arrays where you actually put power to both elements or whatever elements you have. And then there's passive or what's called parasitic antennas, which are your standard high gain antennas, Yagi antennas. Here's some of these. Yeah, smash that away. Smash that away, please. Oh, there.
You got a Yagi there, there you go.
Okay, this is a 900 megahertz high gain. Yagi. Has one driven element here, and that one back here is called a reflector, and these are directors.
Oh, okay, this is the one driven.
Yeah.
This is called a deflector,
Reflector,
reflector, and reflectors.
those are directors.
Directors.
Yes.
Got it.
So, the driven element is resident, that's a halfway lit dipole there.
Okay.
And they folded it there, that's raising impedance there, because whenever we have other elements near it, it's going to generally lower the impedance.
Oh.
They have to compensate for that, so by using a folded dipole, impedance is created. But that doesn't help understand the actual radiation better. So we can just use a dipole there.
I've seen a lot of those. Okay.
And if we put an element that's slightly longer than that, that's going to absorb a certain amount of energy from here. But because it's somewhat longer, there's going to be a phase shift. So it's going to be partly absorbed by that and then re-radiated. But if we adjust the length of that to compensate for the phase shift, then it's going to reinforce in this direction. And then we do the same thing on this side, except they're shorter. And because you want a radiation to reinforce this direction, not there, and you can use multiple radiators. Some antennas can actually have a couple of reflectors, but generally not. It's really complicated mathematically, certainly.
That's why they get shorter.
Yeah,
most
progressively shorter, yeah. Now, a lot of antennas here, they'll get progressively shorter up to a distance, and they'll straighten out.
Is that like the old TV antennas?
Well, the TV antenna is log periodic, and that's a little bit different. It's actually
Yeah.
see, this is actually this was a hybrid log periodic.
That's a receiver.
Yeah.
Or it's actually transmitter.
Yeah, well, it's reciprocity. It wouldn't matter.
Reciprocity,
Yeah.
boom, yeah.
It works out for either one.
On that,
most
where
of your
would the
TV
dipole will be?
Yeah, most of your TV antennas are designed to run over a very wide frequency range. So
Sure.
a Yagi is only like that 900 megahertz. That'll only work at that frequency.
Oh, really?
Yeah. So a high gain Yagi antenna is designed either for single frequency or very narrow frequencies. Where TVs, you had to cover all the TV channels, you know.
Right.
So to get any kind of gain at all, you had what's called a log periodic, where all the elements are driven. Now that one there was part of a hybrid there. That's not neither a full pair. That's it's not.
So you say they're all driven, means there's a dipole?
Oh, that's a driven element. And there's actually a folded dipole.
Uh-huh.
Yeah, folded dipole has 4 times the impedance of a standard
4 times?
dipole. Yeah, so it's 200, about 300 ohms, so 72.
72 times 4.
Yeah.
Wow. Yeah. And,
So anyway, this is how your high gain antennas are designed by careful tuning and applying it. I've got that modeling program that will optimize that kind of stuff. So you did a little bit better.
The higher,
Well,
the higher the frequency, the shorter the antenna.
Yeah.
I see. And folding it, for instance, usually you said the reflector is longer.
Yeah.
But I mean, actually, if this was unfolded, it would be longer.
Yeah.
But since it's.
Oh, no, actually, what you showed, you just cut it off right here at the 72 ohms. So
Oh,
this
I see.
is still a halfway point there.
Okay.
So,
I got you.
So that's only for impedance matching because when you have elements that are close to a different element, it's going to bring them much lower than 72 ohms, and it's yeah. So that raises it back up again to a reasonable value. So
is that megahertz?
that's 900 megs. Yeah.
900 megs, yep, wow.
So how do you get, oh, maybe that, just for my simple brain, because we did 7 megahertz. which
Yeah.
is
Yeah. That's
7
HF.
million
Yeah.
divided by,
Frequency wavelength. So
300
Yeah.
million.
yeah. So I figure
So
so
you
this
had
is
900 megahertz, so wouldn't that be 900 million?
yeah.
So you divide 300 million by 900?
Yeah. So it's going to be a third of a meter,
Okay.
So a
which is
foot,
about a foot. Yeah.
12 inches.
But you cut it in half.
one-
That's
one-
wavelength, so you take half of this. So it's going to be a half a foot. Remember, wavelength,
Oh,
a
half.
dipole's half of a wavelength.
So you'd only need a 1 foot long antenna to have a full
Yeah.
wavelength.
Yeah.
Okay.
So 6 inches would be that.
Yeah.
Crazy.
Uh-huh. Why did we take half of that again? What did we do? Or
That's your fundamental dipole length,
yes.
and put the generator here.
So we're doing halfway.
Halfway point, yeah.
Oh, right. Right. What the full wavelength was.
Now I talked about two different classes of loop antennas. That's a small loop where the dimensions are much smaller than a wavelength. Usually it's much less than a tenth of a wavelength in any dimension. It's considered a small loop. There's also full-size loops, which is generally a full wave. And
Right.
and the directional characteristics, unlike the small loop where it has maximum sensitivity going this way, this is going to have maximum sensitivity broadside to it. And it actually acts almost like you have two dipoles here. This is a full wave on either side, so we've got a quarter wavelength on each leg. And so between here and here is about a half wavelength. Here's about halfway. So this comes out being about a quarter wavelength vertical spacing. And that gives you a little more gain than a dipole in free space. Called a quad antenna. Very popular for HF broadcasting and stuff. The shortwave broadcasting is a lot of that. Well, that's your large loop. Your small loop again.
Small. This would be for small loop or large or both?
This is large.
Large.
We call it a large loop or a full size loop.
Okay.
And it's resonant. Whereas that little guy up there is nowhere near self-resonant. He's very, very, way too small to be so that we have a capacitor across to tune it. So it acts almost like a lumped constant circuit, so it's actually closer to what you have there. So we have distributed voltage and current across the line there. We know that what happens here doesn't happen there because this is spaced away. It takes a while for a radio signal to get from point A to point B. So probably when I'm going to be, I want to ask, did you guys want to be here on, let's see, what was it the day before Christmas? What was it? Day after.
Right.
Well, I'm going to be gone the day after. Did you guys still want to come in then or not? Or do you just want to cancel class for that time? Kevin can substitute. But
I'll let you guys, I mean, I can be here, but it's probably better to.
we'll just take that day off.
I'll be in town, but yeah, whatever
would just take that day off.
Yeah.
There's too much other stuff happening, so, yeah.
Yeah, that'd be nice.
Okay, we'll take next, well, that's,
Got me by surprise, too.
yeah. Okay, we'll take that off. And then the one after that, let's see,
Next Tuesday, yeah.
tomorrow, Thursday, the 21st. Tuesday, 21st, so, yeah, so, a week from the, so, yeah. So, yeah, a week from today we take off.
Okay.
Yeah.
And then Thursday, we're here.
Yeah.
We are, okay. Day after.
That's far enough.
Yeah.
Far enough away from Christmas, it shouldn't be.
Right. Yeah, that works.
Okay, we'll do that. Let's see. Any questions so far? All making sense?
Wow. It's a revelation.
Maybe I should give you, how do we measure radiation resistance?
Oh,
You can't use an ohmmeter, right?
Right.
It only works DC, right? So what do we,
you said something earlier, we're using a double, what did you say? You told us earlier, and I forgot the word. Huh.
Remember talk about the Varley Bridge used for telephone companies to find out where a short was on a telephone pole 100 miles away?
Yes.
Well, what we can do here, and this is variable, and this has a dial on it that tells you what the resistance is. And our unknown is some antenna. We'll connect that to an antenna here. And we put a signal generator in here.
Okay.
And then we have a null detector here, basically just a galvanometer that tells you when you have current flowing or not. And we'll make these two resistors the same, and we put a signal in here, and we adjust this until we get a null. And then when we get a null, we know that this value of resistance has got to be equal to that.
Ooh.
So then we measure this, or we have a dial on already, and then we know that this is going to equal to the radiation resistance of the antenna.
What do you call this?
It's called a RF bridge, or
RF bridge, that's good.
impedance bridge. Now, so far, we've talked about antennas that are self-resonant, meaning that, well, what's the nice thing about resonance? What's the very definition of resonance? Going back a few weeks, a few days anyway. What's the definition of a resonance circuit? And we remember we derived even now to figure out the resonance frequencies.
Isn't that when
Very definition is, what was that?
I can see it in my head, I'm trying to think of the terminology, because unfortunately, that's what,
It's where, at the point where the maximum, oh,
There.
okay.
Capacitive reactance equal to inductive reactance.
Uh-huh.
Now, we mentioned that in an antenna, we no longer have lumped constants, we have distributed constants. However, we can compensate for them with lumped constants. In other words, we can measure it and it'll look just like it's lumped constants. Just like with a bridge here, the resistance isn't something that we can just say they're here.
Just one spot, it's all over.
It's all over, so we use bridge here. Well, in this case,
Huh. Uh-huh.
we've always assumed that the antenna is resonant up to this point. Okay?
Resonant.
We're halfway, the antenna is resonant, and
Okay.
it follows the same rules. As if we look at the impedance at the feed point there, we'd find that the inductive reactance and capacitive reactance cancel out exactly.
Mm-hmm.
Now, what happens if you get an antenna shorter than wavelength? What does it look like? looks like an antenna is too short.
The impedance would be, higher. Well, let's see, because
Well,
the,
which
capacitance-
direction?
Which direction, yeah. Are you asking for the radiation pattern?
Not the radiation pattern, no, just the impedance. What's the impedance look like for an antenna that's too short? No, we won't make it dramatically short, just a little short, a little too short.
Are you asking like the relationship between the,
Yeah, what's going to be bigger if we make the antenna short?
gosh, I keep going back and forth in my head. It's the capacitance or the induction.
Electrically, an antenna looks like this.
Okay. Aha.
Okay.
It's going to look like the capacitor is bigger.
Oh, capacitive reactance is big.
Capacitive reactance.
So the antenna is short or too short, it has, this goes up.
Yeah.
If it's too long, this goes up.
Why is that? Why do you, I mean, it kind of makes sense, but
It's because, remember the Eli the Iceman?
yes.
Okay,
Yeah.
so. In a capacitive reactive circuit, which comes earlier, like inductance or capacitance, or the voltage or the current. We'll talk about voltage or current.
Which comes first?
Mhm.
Which comes earlier?
Yeah.
Oh, wow. Oh, right. That's when we did the experiment that showed one was like 90 degrees of.
In a pure reactive. So, well, what's going to happen is it's going to want to find a resonant frequency no matter what. So if it's not. So what happens is this current can't extend off the end there, right?
Right.
You can't do it. So what happens if we look at the normal distance of current here, this is going to want to have to go somewhere, okay?
Right.
So what's going to happen is it's going to reverse itself this way here. So what we now have is you have the current is going to be shifted even further relative to the voltage. So we have
The
to
current is, yeah.
So we look back here. This is now going to we're going to have a shift in this direction. So the current is going to be delayed by the voltage here.
The current is delayed.
Yeah.
Okay.
Now,
Wow.
but what makes it a little hard to conceive is because we're now distributing this across a distance. We're no longer looking at what's happening at a point.
Right.
However, it will be reflected back to what we see at this point. So what it comes out to be is if an antenna is too long and you want to compensate it, you would add some inductance. If the antenna is too, if you add the antenna is too short and you want to compensate it for it, you add inductance. If it's too long, you add some capacitive reactance to it. So, now, what's a typical wavelength of AM broadcast? Let's pick in the frequency in the middle of the AM broadcast band. So that's nice round 1 megahertz. 1,000 kilohertz for 1 megahertz. What's the wavelength of a mid-band AM radio broadcast signal? 300 meters, okay. Now, you've got the other end, you got a little whip that's maybe, 3 feet long, okay? There's one car radio. Okay, what fraction of a wavelength is your car radio antenna?
Oh, yeah. It might be a meter.
Might be a meter, okay?
Yeah. So,
So it's a 300th of a wavelength,
right.
okay? What's that gonna look like electrically? You see the whip here. What's the impedance gonna look like at the base of that?
Impedance. I would say
Which-
high.
Well, it's gonna be very high, because capacitor reactance, okay?
Capacitive reactance is
Yeah.
high.
Yeah, capacitor reactance is very high, so what do we do to make that thing resonate?
Like you said, add inductance.
Right, we put a loading coil in. Front end of your alien receiver, have a loading coil.
Huh.
Now, there's one other thing though that happens. What's the radiation resistance of that?
Oh,
We didn't even talk about which direction it goes as you shorten the antenna.
I mean, I would assume that the most efficient radiation resistance would be at that halfway point.
That's generally true.
I would assume, so if you get off of that in any direction, I would assume the resistance would go up, but I don't know.
Radiation resistance, car radio is maybe 1/10 of an ohm.
Really?
Yeah.
Wow.
So the resistance goes down as the length of the antenna relative to the wavelength. So
Interesting.
you got this really teeny tiny radiation resistance there. So how do we match that? So your receiver is happy.
How do you match that? Oh. You need a certain.
Oh, what you actually do is you put a tap on this inductor here.
Oh,
You're feeding it right here, because at this point it's extremely high impedance. So down at this bottom is 0, okay? So we pick a tap point somewhere on there where the impedance is usable, what we would normally want to have in a receiver there. So.
okay. And it moves up and down, or that's.
Yeah, well, it's in factory adjustment, they move it, so it's a tapped inductor.
Which is like that one you
Yeah.
showed us.
Now, here's another thing about that. What do we know about, or how do we define Q? What is Q?
Q.
Written down somewhere.
I know. Probably one of last week's notes. What was Q? Q was the,
What's the importance of Q? What does Q practically tell us about a circuit? Especially resonant one.
all right, what was Q again?
Q is quality factor, okay?
Quality factor.
Quality factor, which is how sharp the thing is tuned.
How sharp it's tuned.
Oh, that's good. I probably only have one viewer anyway, it would be Kevin. We'll stay up next by,
That's
go
why
through
I put later on
week,
millions
so,
of views.
so, thanks for coming down my door.
Sorry,
Oh, no
I'm
problem.
getting down here and I got this call.
No problem. This is pretty, if you look at the end of the YouTube programs, they never even have a camera guy, so, right?
That's right. It's all
That's his face there.
Yep.
Is it? Did you guys get something to eat?
I'll say it. If you want to bring me a plate, I wouldn't fight
Save my
you.
cookie, yeah. We could have a cookie.
I don't have any home baked ones, but I do have these madeleines. Have you ever had madeleines?
Sure, whatever you got. I would love that.
Thank you, Julius.
Man, wow.
Some service here.
Hi, yes. Remind me again, where were we using Q on what circuits or what?
Untuned circuits, resident circuit, we're going to show the bell curve.
Yeah.
It's got high Q, it's very narrow.
Oh, yes.
Okay.
Oh, okay, all right, now. yeah.
Okay.
Yeah.
Now, remember it's X over R, right? And generally X of L over R. Okay.
Okay.
So if R goes down to nothing, what's going to happen to the Q?
It's gonna go very high.
Go very high, which means this is going to be extremely narrow tuning, which it is.
It is.
Yeah. So
Yeah.
a car radio, your front end there is tuned dial has an adjuster on that antenna, make it track. So yeah, so you have
Q
very
is X of L
Yeah.
over R.
Yeah.
Yeah.
Now, if we didn't have a loading coil, we would no longer have a high Q circuit, but we would have a very lousy circuit to start with. So the sensitivity would be a nothing, so we
Wow.
resonate this, so we now can get some
Uh-huh.
actual power out of it, and then we can match that, and then use a tuning of the front end to
And again, what we're putting there is an inductor,
an inductor. Yeah.
like a variable inductor.
Yeah, it's got a slug tune inductor. So we'll take apart some car radios at one point here. Now, what happens if the antenna's too long? Well, what's happening is we now have a current reversal at the end here.
Right.
And it's going to mess up the pattern a little bit, but what's going to happen is it's going to have to go this extra distance before it reverses, so it looks like it's longer, and there's more delay time, so we're going to have more inductance there. More inductance, so the antenna's very long. We can add some capacitance there. Shorten the antenna.
Enjoy.
And
Do
this
we
case,
have wow.
and this is called, this is not surprisingly called a trimmer capacitor.
Trimmer.
A
Yeah.
trimmer, yeah.
If your antenna's too long.
And that's a loading inductor. So you can load it and trim it.
And so let's say you could have these on you could have both on any antenna,
You could.
and that would help you
Yeah.
tune.
So that's what this guy is. This guy will tune a coat hanger in almost any frequency. So
That's a coat hanger. I love that. Okay. For sure. Oh, and if the antenna's too long, the relationship between voltage and
voltage curve's going to swap the other direction.
the current would come
Yeah.
first.
Yeah.
And voltage would.
Yeah.
Right.
You love the ice band. Always works.
Yes.
Whether it's lump constants or continuous antennas. Okay, well, now we got some fundamentals of how antenna radiates and how it deradiates or absorbs energy from space. Right? And obviously, the more antenna you have out there for a given wavelength, the more you're going to be able to absorb. There's a factor called capture area, which is if we look at this radiating, expanding farther away, the larger the antenna is relative to that, or I should say, the percentage of it that you can absorb with a given wavelength antenna is going to keep decreasing. If we were to make the antenna proportional to the surface area there, the thing would get very huge as it moves further away. But there is an effective number called capture area, which is what the effective size of your antenna is relative to the surface of the wavefront. So we usually measure antenna field intensity in what's called, well, it's either microvolts per meter or millivolts per meter. It's the voltage that we induce across a 1 meter long antenna. So then we can use that for measuring the actual signal.
Micro or millivolts? Or
Yeah, microvolts or millivolts, depending on how strong a signal we're dealing with to start with. But it's the intensity field is a voltage per linear foot. There's a couple other ways to measuring that when you get into microwave. It can be actually practical to measure the actual surface area of the antenna, like when you have a parabolic dish, which actually has gain in both vertical and horizontal, even though its polarization is only in one direction. So there's half parabolas, which are just parabolic ones in one dimension, so which are actually a little easier to calculate. Okay, so what do we do with the signal once we receive it? Well, let's talk about.
do we have to amplify it somehow?
Yeah, amplify it. Now, you don't have to. A crystal radio, if you have a really strong signal there, all you need is a headphone and a diode, you know.
Whoa.
But, but that's assuming that the signal is very strong. Actually, it'll work on this. We got a 970s right down the road here, and you can pick that up pretty easily with a diode and a headphone. But let's talk about a little more, more refined radios and what we need to do to receive signal. Let's talk about some actual power levels. Now remember, I'll let you guys do some calculations. This is going to be fun.
Ooh.
Now remember we talked about decibels before.
Oh, yeah.
So how do we define a decibel?
I remember the measurement was like geometric or expand.
Yeah, it's 10 times a log.
Logarithmic, yeah.
Or P1 over P2, or P2 over P1. If it's greater than 1, then you'll have a positive log, positive dB. If it's less than negative. But before you even do that, let's get a feel for what radio signals are. So I've got a communications receiver there. This is, it's a pretty skookum radio receiver, but it doesn't have a whole lot more sensitivity than what it had 7 years ago. The important thing is to get an idea of how much signal we're normally receiving. So,
Real quick, before that equation that you just put up, what was P2 and P1? What was
P1 is the input power, and P2 is the output power. And if we got an amplifier, that's going to be a number greater than 1. If it's attenuation for the signal loss, it's going to be negative. Come out negative. So what did we say circuit-wise is a receiving antenna? What does a receiving antenna look like? What's its functional equivalent? And we absorb radiation from the space to the sky out there. Looks like a generator.
Aha.
Then we got to go into something. What do you think would be a good thing for that to go into?
Well,
Okay, we'll start with the amplifier. Now, look from very practical, don't overthink this. What are you trying to do on a radio receiver? What's your function? What's that?
detect wavelength, frequency, detect
Well,
a signal.
if you're somebody who'd never seen a radio before,
Right.
and you handed them a transistor radio, it says, and explain what it's for, okay? Well, how would you describe what its purpose was. And what the controls are on it.
You want to be able to tune into a certain frequency.
Okay, very good. That's one function there.
And then detect a signal on that frequency, and then you want to amplify that so that you can know what that
Okay.
signal. Yeah.
So, one of the important things, probably more important than amplification, is selectivity. Pick a frequency, right?
Right.
Otherwise, you just have an amplifier, it's going to amplify everything out there. So.
Right.
And most of the time, we don't want to hear every radio station at once, so
True.
we need some means of selectivity.
Right.
So, we can do that right in our antenna in a car radio, since we have a very high Q antenna to start with. We've already got quite a bit of selectivity already happening. Just by
Right.
virtue of the fact the antenna is so small and the Q is so high.
Mm-hmm.
But so we did, let's say we had a full-size antenna. For example, in shortwave stuff I do here, I'm usually using antennas that are pretty close to a resident long antennas. A bit of intercept area that they have. So a typical receiver there, a strong signal is considered to be what we call an S9 signal, and that's equivalent to 50 microvolts across the antenna terminals. Now, that's not chiseled in granite, but it's a pretty long-standing standard for communications receivers. So 50 microvolts across the antenna terminals, and we generally have an input impedance of 50 ohms, and we explained that 50 ohms became standardized for a lot of practical reasons, but basically it's kind of in the ballpark of where an antenna is going to be in average height. We have 50 ohm input signal here. Now, this is real power. It ain't very much, but it's real power because we're doing real things with that, right?
Right.
We're taking energy off the antenna and we're doing some real work with it.
Yes.
Now, we may not see the work till we get it amplified enough to start moving a loudspeaker around.
Right. Right.
Still doing some work here. So first thing we do, let's get an idea of how much power that actually is. So I'll use 50 microvolts, and this is a strong signal. And S9 is a good strong signal. It's not weak signal work. No, it's just what we call pretty much undetectable noise in the background. Okay.
Mm-hmm.
FM broadcast, right? At least AM broadcast call it. So we got 50 microvolts there. Tell me how much power that is, actually input.
Sure. Man. Power?
How much power?
Well,
And you can both collaborate on this.
resistance is 50. Volts. Okay, VIR. Okay, so we can figure out I. And micro is what? Million?
50 is micro is a million.
It's a million. Point, 10, 100, 1,000, 10,000. I think E divided by 50 ohms. Okay, that will give us I, and then we plug in I into pi, right? That will give us power.
Okay,
Right? Am I doing that? Am I using the right?
how do we, if we know the resistance, we know the voltage,
Okay.
how do we figure out power?
Oh, well, we had it. There you go.
Okay, so how much power is that?
Let's calculate it. You want to calculate how many zeros is that? Let's see. I have 1, 2, 3, 4, 5 zeros before. Is that right?
Let's see, 15, that's 5, 4 zeros.
Is it 4? Okay. Because it's tens, hundreds, thousands, 10,000s,
What zero?
100,000, millions. Is that it?
Yeah.
So it'd be 0.000001.
Wait, count those for me. It's tens, hundreds, thousands, 10,000.
So this would be 1,000, this would be a million, and that'd be
Oh, okay.
50 millionths.
Thousands. 50 millions. Okay, all right. That's where I was off there. Okay.
Divide that by 50. You get 0.000001.
You square that. You can square that.
1.
Oh, that's
Okay, we got to square it. 1, 2, 3, 4
That's not right.
times 20.
Remember, when you square a decimal, it becomes even more decimal places.
Divided by 50.
I don't know what that means.
There's going to be 11 zeros
Okay,
before the 5.
okay.
What does E-9 mean?
Oh, is yours
to the
2-9?
10 to the minus 5.
Well, that's nice.
10 to the minus 9 meaning 9 zeros. Oh, E,
Is exponential notation.
exponential, right. Wait a minute. Is that right?
So you divide that by 50?
Is that right?
Yeah. Well, it looks right.
E. So how many zeros are we talking here?
Let's see. 2 to the minus 9. Okay, so it's 9 zeros to the,
Right.
yeah, so it's 9 zeros.
And then when we divide
And
by
then you divide by
50,
50
it's
to the 11.
11.
11 zeros.
11 zeros. Okay, okay.
Wait, what?
11 zeros. It's point
So it's
11 zeros
and
and
then
then 5. Yeah. Kooky, isn't it?
And that's in watts. It's not a lot of watts.
Not a lot of watts.
And that's a strong signal.
Wow.
And so you'd have an AM broadcasting at a reasonable distance. So we have to get that up to a level we can hear. So let's do it scientifically.
Okay.
Ma Bell, back about 100 years ago, figured out what a nominal audible level is. And back when this is state-of-the-art telephone here, okay? And they, on a typical earphone like that, they found a good, strong, not deafening, but a strong, comfortable listening level occurred, and you had that headphone there, and it was fed with minus 13 dBm, decibels relative to a milliwatt, or if we want to go backwards, a milliwatt is a thousandth of a watt, so it comes out to be a 20,000th of a watt. So we have point 0.0002.
02. Tens, hundreds, thousands, 10,000. Oh,
And we can convert that to watts. So 20
and how many, okay, go ahead.
minus 13. So minus 10 dBm. A dBm is 1 milliwatt. 10 would be the next one down here, and then another, half that. Oh, I'm sorry, that would be 5.
Oh,
0.0005 watts.
okay. Makes
So-
it comfortable, okay.
To a comfortable listening level with a standard earphone.
Wow, that's pretty low too.
Yeah. Well, you hear these guys with these earbuds with like a watt in there, and you wonder why anybody has any hearing left, you know?
Yeah, well,
Because this is you're down in your milliwatts, which is,
Wow.
that's a strong resistance. So, anyway, so what do we have to amplify this by to get to that?
oh, let's see, how many zeros is that?
Yeah, how many zeros do we want to get rid of?
How many? Let's see, well, 1, 2, 3, 4. And that's what, 11 there? So
Yep.
we want to get rid of 7 zeros.
Mm-hmm.
What is that? Let me see. 5, 6, 7, 110 million,
10 million, that's right.
right?
Yep.
Okay.
So we need to get 10 million to 1 power gain
Okay.
between the antenna and that's not even putting a speaker on, that's for the headphones.
Right, yeah.
10 million to 1 power gain. How many dB is that?
Oh. Well. Ten log. 10
Log of
is
10 million to 1.
right.
EB, what is log again?
Common logarithm, log to the base 10. So you just punch the log in your so the log of 10 million is what?
dB. Okay. We're getting there. This class should really be in the morning when I'm maybe noon. Maybe noon. After a full day. But I'm loving it. But yeah. Ooh, okay. So we're saying. Do I have to put 10 log or just log?
No, you do the log first.
Do log of 10 million.
Log of 10 million. Then you do times 10.
Okay. 70.
Yep, 70 dB. Good round number. Something we all, very common. We all have that same number kind of embedded in our head if you're a radio guy.
Sure. That's a nice, good level of full reach. Wow.
So somehow between our antenna and our earphone, we have to get 70 dB of gain.
Okay.
Now,
Okay.
several places we can do that.
Tubes. Transistors. What?
I'm going to bring something out.
Something to the power of. I'm trying to get exactly the definition, but it's when you say to the function. It basically describes an exponential function, something like doubles and it doubles and it doubles. Have you ever seen that? Like the expansion of the population of rabbits. Like 2 rabbits still have 3 babies.
This is a regenerative receiver.
And it just grows exponentially.
Okay. 100 years ago, we did that 70 decibels of gain in one stage because very few people could afford more than one tube.
Wow.
And the way that works is it's an oscillator just on the verge of oscillation. You know, we were talking about amplification, how a tube amplifies.
Yeah. So they did in one stage, huh?
One stage. They had a tuned circuit out here.
Okay.
And you had your antenna connected here,
Oh.
and whatever the grid does is your input signal. And you had a small sampling of this fed back into here.
Huh.
That's called a tickler coil. And actually, this is an advance over the tickler coil, although I do have, no, it's not. Here it is. There's a secondary coil right there.
Oh, you're right. It comes in through here. Is that it?
This small portion on top.
Oh, that's it. Oh.
And what it would do is, remember we talked about negative feedback when using op amps, use negative feedback to set the gain. This use positive feedback. Use just enough so this is just on the verge of oscillation. When an oscillator is just on the verge of oscillator, it'll keep going without any input signal, by definition. Okay, you're causing to think that that's how we generate radio signals in the first place. So this is just like feedback. You want an amp if the microphone is running at it generates its own signal. So it generates its own signal. If we adjust the gain just below the threshold where it oscillates itself, it approaches infinite gain.
Wow.
So you adjust this to just on the verge of oscillation and you get a nice 70 decibels of gain. Actually pretty easily.
As it
With one.
starts approaching infinite gain,
Yeah.
you just want to get it right there at
Yeah.
70.
And does it pretty nicely, very simply. And
Wow.
we've been doing that for 100 years. Okay? So all your gain is right up at the front stage. Now,
Wow.
as receivers became more and more sophisticated, we moved the gain further and further downstream.
Did we?
Yeah. So your state-of-the-art receivers, including cell phones, now are pretty much what we call direct conversion, where most of the gain is after detection. So,
Wow.
we'll
And gain, you mean gain of decibels?
Amplification,
Gain of
yeah,
ampli- Okay, yeah.
most of that is done
Wow.
after the detection. So
They're working with such little microvolts, detecting it, and then,
Yeah.
and then at the,
now on a cell phone, rather than 70 dB down, or rather than 50 microvolts, we may be working at a fraction of a microvolt.
fraction of a microvolt.
Well,
Yeah.
fraction of a microvolt on cell phones.
Wow.
This again is a strong signal for like an AM broadcast.
Right.
Down there. And we'll typically have gains of on the order of 120 dB.
Right, that would mean,
So let's talk about the evolution of receivers for a bit. This didn't all come in a vacuum. Well, we did a vacuum tube.
yeah.
I guess
It did.
It did arrive in a vacuum. But,
Okay, again, okay, yeah, I'm gonna have to go back and look. The vacuum tube increases.
we use positive feedback. And so
It increases volts or what?
it increases the gain, the amplification.
Yes.
So we start with a minuscule signal and we amplify it by
Oh.
recycling.
Right, okay. Yeah.
And again, since tubes were very expensive, you had to get as much gain as you possibly could out of a single tube, you know.
Right.
Had a lot of dog walking money back 100 years ago.
Oh, yeah. What's the disadvantage of doing it all in one stage versus if you
Yeah.
had money and you were a government?
Yeah. Well, let's talk about it. First of all, in order to make that thing work, you had to have a safecracker's touch. You just didn't plug it in. Okay, it was not a user-friendly thing. So
Right.
people
had
who
to
were doing that
adjust.
were radio amateurs for the most part that knew how to adjust right on the very edge. You know?
Right here.
Yeah.
Yeah. Wow.
And so to make it a little more user-friendly, we had to make some modifications. There was no, even nowadays, there's nothing more sensitive than a regenerative receiver. It's not even in theory. You can't even get better than that. Because, not only in theory, but in practice, at the verge of oscillation, it's got infinite gain. And it also has infinite Q. It's infinite selectivity.
Oh, wow. Yeah.
Pretty cool.
Yeah.
But again, you pay the price. The price is being able to balance
Yes.
like balancing
Oh, right.
something on the edge.
Right on there.
Right on the edge there. So, to make it a little more tame, we started moving toward the tuned radio frequency amplifier, where we had multiple stages, each was tuned together. I have one upstairs, my sister has one upstairs, a three-stage gain neutron receiver, which was 100 years, it's 100 years old this year.
Wow.
And people were paid $1,000 for those back 100 years ago. I mean, you didn't get a big screen TV, everybody gathered around and watched the radio, you know, because that was a little bit of entertainment. But they had 3 tune stages, so rather than doing it all in one stage,
Right.
you distributed the gain over multiple stages. So you had 3 tuning dials in it, you know. And so they're all tuned radio frequency amplifiers, tuned at the incoming frequency. Well, that's great as far as it is, but what happens is, first of all, you have to tune all of them 3 separately.
Right.
And that was a little complicated itself. It wasn't quite as touchy as these.
Yeah.
Several companies like Atwater Kent said, let's all gang them all together, so I only need 1 knob, and it turns all 3 tune stages.
Oh,
But there's still the big problem is, the AM broadcast band is a huge range of frequencies.
it is. Okay.
It's a 3 to 1 frequency range at the bare minimum. So what happens is, as you tune to the top, the bandwidth of the signal got wider and wider. So the Q decreased as you went to the top of the band. Well, what does Q have to do? Well, it has to do with the fidelity. You know, the higher the Q, the narrower the audio frequency response is.
Yeah.
So the stations down at the bottom will sound very restricted and narrow, and at the top end you get the high fidelity stuff happening at the high end. You know? So that became, as people became a little more savvy with radios, as this became something that was not acceptable to have.
Right.
The bottom end of the end broadcast band sucked, and the top end was good. So how do you make an amplifier consistent over the entire range of the AM broadcast? So what they did is we do all the amplification at 1 frequency. So you build this thing, which could be multiple tube amplifiers. You don't have to draw all the inner workings here. You have a multiple tuned amplifier, and all tune the same frequency. And it's fixed, okay? It's all the same frequency. Well, that doesn't do you any good if you want to listen to multiple stations. Well, this was not tuned at the frequency you were listening to.
Right.
It was tuned at some intermediate frequency. So we installed what's, well, it was very early in the game, was standardized at 455 kilohertz, which is outside the actual broadcast band itself, which is a good thing. You didn't want that happening inside the frequency. So all we had to do left was convert the incoming frequency into that.
Okay.
So we have what's called mixer stage, and here's some modern symbol for a mixer, but it was basically a tube with, some of them had 2 grids, one for the incoming frequency and one for what we call a local oscillator. Local oscillator was exactly that. It's an oscillator inside your receiver.
Huh.
That was the difference between the signal they wanted to come in. Let's say we want a station coming in at 1,000 kilohertz, okay? We wanted to know 1,000 kilohertz station in. We mix that, and any nonlinear device, including just a simple diode, will take any 2 frequencies, put in it, and give you the sums and the differences out. So we mix this local oscillator in this case we tune it to 1455, which is the sum of these 2 frequencies. Take the difference out, which was 455 kilohertz. So we can amplify the daylights out of it like this and make this bandwidth ideal, you know.
Right.
It could be, have exactly the right
Once you
response.
have the exact, okay.
Yeah. So all we have to do is convert from here to here, and lo and behold, we could have a pretty high fidelity receiver there with lots of gain. It was not touchy tuning because this is already pre-tuned. And then after you do your last stage would be your detector, which extracts the audio from the signal. So,
The audio.
yeah, we'll go into that process a little later. So,
Okay, really back to the oscillator, and you're saying that because it takes the sum of the difference of the
sum and the difference.
sum and the difference.
And the difference.
And what's that principle, or what is that?
It's called the super heterodyne receiver, or superhet, which still 99% of all receivers, whether it's from TV to radar, are superhet of some sort. Now, since one of the fundamental processes of mixing 2 frequencies together, we get the sums and the differences. You see where that might create a little bit of a problem here. Because this would respond not only to 1,000 kilohertz, but it will also respond to 1910 kilohertz.
Oh.
It turns out to be that this is called your image frequency, which is always twice your IF frequency away from what you want. So to
Oh,
find out
wow.
where that would be, you double this frequency and
Add
add
that.
it to that. So this arrangement would also respond to 1910 kilohertz. Now, in the early days of radio, that was no problem because there was nothing there.
Sure.
But as radio became more and more crowded there, we said, oh, we got to do something about that image frequency.
Mm-hmm.
So the only way you can take care of the image frequency is to have enough selectivity here ahead of the mixer, the tune circuit or whatever, so that it would reject that, and this would be far enough away that this could handle it. And the reason, most of your, this one here. These front ends had two capacitors. There's one for the local oscillator, and one was for the selective stage ahead of the local oscillator. So that would take care of that. I've got some.
Oh,
Let's see.
so wait, one's for here and one's for. I'll let him ask him that.
Anyway, that's very typical front end capacitor in
So those oscillators will be connected where on that? What are they? So
well, let's see. Here's they don't have any broadcast cam capacitor. Usually the local oscillators is higher in frequency than the incoming. The
Right.
capacitor plates would be generally a smaller set.
okay. And that tunes out.
Yeah, one of them would be, and these would be ganged together. So you have
Right.
a local oscillator. And anytime you see a dotted line in any schematic, it simply means a mechanical connection.
Okay.
So that means they're on the same shaft. But this one would tune at a different rate than that one there. So it'd always keep that and that the difference apart there. But this would have enough selectivity before the mixer so you could reject that. Now,
Okay.
the higher this IF frequency is, the farther apart these two frequencies are. Right?
Okay.
So
Yeah.
using a high IF frequency, you get better image rejection.
Okay. So it'd be easier to
Easier to do
use
that.
it. Okay, using higher IF frequency for your amplifier.
Yeah,
Okay.
for the IF amplifier. Now, there's a limit to how far you can go. Now, this was kind of standardized in broadcast receivers for many years. It still is for AM broadcast. Car radios generally use a 262 kilohertz of IF. A little more.
Who does?
Car radios.
Car radio.
Yeah,
Okay.
so standard 262. I got some 262 IF transformers around someplace.
Okay.
Which was a little more restricted audio.
Sure.
But because the car radios moving around so much, having extra selectivity was really an advantage there. So you're more likely to, if you're driving across country, to have some interfering signal from.
Right.
So in general, the higher your IF frequency, the better the image rejection is. The ability to reject the image frequency, because this doesn't have to be quite as high as selectivity. There's a limit to how selective you can make a single tune circuit.
Really? Okay.
Yeah, it's about, we're trying to, the Q of about 200 is about the best you can do until you start going to crystals. Okay, so that's great. The only problem is when you start going to communication systems where you didn't want a lot of bandwidth, when it's super narrow, or Morse code or anything else, we have gobs and gobs of stations, especially in shortwave, just jammed together. We wanted more selectivity. So you have another issue. You go to a lower IF frequency, the image rejection is no longer as good,
Right.
but you get better selectivity overall. So
Selectivity. You're
the
saying.
ability to separate two close stations. Okay,
Really?
so the lower the IF, the narrower you can make your selectivity.
Okay.
So what do? We have two conflicting interests here. Okay, we want good image rejection, but we want high selectivity. In some cases, for communications, it wasn't a problem for broadcasting in general.
Sure.
But the next step in receiver evolution simple simplify the schematic even more. It's got more stuff in there. Take a high IF frequency of, let's say, 1600 kilohertz. I'll just draw a square here. That includes all the amplifiers that are tuned to 1600. Local oscillator, which would be 1600 above whatever you have coming in. Okay. So this would be a much higher frequency. So
Okay, what would you want to do?
Let's say, I'll use the same frequency here, so we'll tune that to 2600.
Okay.
And those two, we get the differences out, and we get high enough frequency there that the image frequency would be twice that above that. So the image frequency is 40. Yeah,
42?
Yeah.
Wow.
So
Okay.
no problem separating 4200 hertz kilohertz from here.
Sure.
But now we have a broad, or selectivity is like a barn door now.
Yeah.
So we can't separate closely spaced stations. We got rid of the image, we can't base the station. So what we did is we had another IF frequency, and this is usually around 50 kilohertz.
Oh.
And you get really high Q circuits at 50 kilohertz. But it didn't mean that you had a local oscillator, which was the difference between here and here. So this would be at like 1650.
Okay.
And the differences between there. Now, the reason you didn't have any images is you weren't allowed any images through here. All your images were already taken care of before they ever got there.
Okay, you're just getting one
Yeah.
frequency.
Yeah.
Yeah.
There's no possibility of that. So you use
It's
the
all
low IF.
left out. Okay.
Low IF.
Interesting.
And then here, this would go to your final detector. And lo and behold.
Okay.
So that's a dual conversion receiver, which is just about everything I got here is a dual receiver, dual conversion receiver. So that's the evolution of communications receivers.
Very smart.
Took a long time to get there.
Yeah, I think it takes a really deep understanding of all of it. Just understanding, there's a, like you said, there's the image frequency.
Yeah.
I mean, probably somebody didn't recognize that right away through mathematics. It's just they recognized.
Well, actually, Fourier did.
Oh, he did?
Yeah.
Oh, wow.
In the 1700s.
He did. Well, then.
Well, he didn't have any radios to worry about, though. So.
Wow.
So the whole idea of the harmonic generation and deep frequencies was well known by then. You just didn't know the application to electronics.
Application, right. Okay.
Joseph Fourier was one of my heroes, despite him being French.
Oh, yeah. How do you spell his name?
Fourier. And he came very close to getting decapitated during the French Revolution, for not being revolutionary enough, but he managed to evade it. As opposed to Antoine Lavoisier, who was the guy who discovered oxygen, who was decapitated during the French Revolution.
Oh, wow.
Because he decided to get involved in politics. So the lesson to take away here is if you want to be a scientist, don't get involved in politics. Because
Don't get involved?
then, yeah,
Get involved.
because, Lavoisier did very little science after his beheading. You know,
Oh, yeah, you're right. Well, science seems to be very political these days.
Yeah, yeah.
And what, okay, and Joseph Fourier.
Fourier.
He did.
He had Fourier analysis, the fast Fourier transform they use in digital audio processing all the time, convert from analog to digital. That was all Fourier.
Wow. Back then.
Yeah.
He didn't even have that equipment.
He didn't have it, but he had the math to do it.
He had the math. So he's a mathematician that studied frequencies and.
Yeah.
Wow. Okay.
And with things like ringing bells and all that. He wasn't really doing it, but he was way ahead of everybody else.
Can you imagine even before he
Probably not figuring all this out.
even right now. Wow. I mean, I'm gonna have to go back and just think about it. About every 3 or 4 minutes, you hit me with something that I know I'm gonna have to study for an hour or two. I mean, really. Okay, we'll get back to that later.
Okay, now, we've built some audio amps before, well, they were DC amps, so they basically audio amps. And an RF amp is just an amplifier that's tuned to a specific frequency. So now we haven't talked about detection. So the first form of AM or radio was actually AM, and it's very fortunately that we have a very strong AM station here, because you can see our AM signal right here. And then
There we go.
we got a carrier, and then we got the modulation on top of it.
Tell me about modulation.
Well, that's the actual information. The carrier is actually the radio frequency. The
Oh,
radio
okay.
frequency is 970,
Okay.
970 AM. And the information you put on it changes the amplitude. So we
Oh, wow.
vary the amplitude in accordance with the
Oh,
stereo.
I see. So it's not a perfect.
No, it's changing all the time. So the first way of putting voice information on radio is amplitude modulation. Now, it's not the only way to do it, but that's the oldest. So that's what AM stands for, amplitude modulation. So we do that. Well, the crystal radio is nothing more than a demodulator. It's got a tuned circuit, and then you got some sort of detector. Nowadays we use a germanium or silicon detector or any of it. Back in the early days of radio, you used a cat's whisker, which was just a chunk of galena and a little wire that you moved around on until you found a sweet spot, and at that point it became a diode. So you just made this diode on the fly.
What's galena?
It's a lead ore compound, which is a predecessor to older semiconductors. So, crystal radio was simply a tuned circuit, and he used to make, he used to always play around with these razor blade radios. Gillette used to make these blue blade razors, and you take a pencil lead and Gillette bluing on it would also form a semiconductor. So you take a set of headphones, a piece of wire out there to pick up the station, and then you move the diode around to get the sweet spot, so then you could demodulate the audio and extract it from, say. So
When you say you, that means only you. And who else was doing that as a kid?
all of us.
Yeah, really? Wow.
That was every kid had a crystal radio when I was a kid.
Man, wow. Mm.
So here's an RF carrier.
What happened to our childhood?
Social media.
Yeah.
Cartoons.
There's a carrier, some radio frequency, okay? Not much information by itself. You can turn on and off. That's what Morse code is. You just turn the carrier on or off, very simple. To put audio on top of that, what we do is, let's say this is an audio frequency, very simplified. So there's a low audio frequency. So this is in the megahertz range. This is a few kilohertz maybe, okay? So we keep the number simple. We'll make this carrier at 1 megahertz or 1,000 kilohertz. And we'll start with an audio signal of 1 kilohertz. So our RF carrier is 1,000 times the frequency of the audio information on that. So what we can do here is we can change the amplitude of that in accordance with this. So we use this to control the gain of an amplifier. So we take a radio frequency amplifier and we have RF going in there, and then we mix, and a mixer is nothing more than any nonlinear device. A diode can do it. There's more elegant ways of doing it, but any nonlinear device, in other words, any device where it does not follow Ohm's law strictly, where the voltage and current are not exactly proportional, you can get differences between it. So this is a general symbol for a mixer. And just like we use it for down converting our radio frequencies to IF frequency, same thing will allow us to convert, or allow us to modulate this amplitude with this. So we can take this signal here, put it here, and now we have a composite of this, which is a radio frequency which increases, the amplitude increases and increases, so the frequency stays the same.
Yes.
But the amplitude, so what we want to do is recover this. When we receive, we want to recover the outline of that.
Okay. And that
So
gives you-
this is this is our neutral plug here, and it's going through space. So we need to detect this envelope here, okay?
Right.
So we need to build the amplitude. And the simplest way of doing that is just to wipe off the bottom half here.
Mm-hmm.
And that's you just use a diode to conduct one direction to the other.
Right.
So that's our fundamental diode, is your AM detector. Wipe off the bottom there. Now we still have this RF in between, but that's so far different from the RF, from the audio. It doesn't really bother things most now. And if you're amplifying it, you do want to get rid of this. But even by itself, you just take this signal here, put it into a headphone, and you have audio.
That's basically at an audio wavelength.
Yeah.
Frequency.
The outline of this is audio,
Right.
whereas this is carrier.
Wow.
Frequency is
And you can get all those rich tones and everything through. The end.
So that is the generation of AM, and in detecting it, all you have to do is rectify it and pull it back out. Now, like I said, that's very crude, inelegant way of doing it, but that's the way it was done for many years till we figured out how to amplify things. Think about a diode detector, crystal radio, you don't need any amplification. You rely on the power of the incoming signal to do everything for you. Because nobody had any amplifiers then. Everything was passive. Vacuum tubes didn't exist in the early days of radio.
Mm-hmm.
It was using spark gap. Showed you how I could resonate that circuit with just a battery and shock. So that's how they generated radio. And the detector is pretty much equivalent on the receiving end.
So like, for instance, in this signal, it looks like the way it has, even within the frequency, there's,
Yeah, well, there's also some AC hum on there, but
I mean, even, okay, obviously you can see the frequency, but even within that, it looks like there's,
yeah.
is that anything? Is that information, or is that, that's not really?
That's information. Let's see.
So what, I guess what we're saying is, this frequency can have little dips in it like that?
Well, that's AM. So the fundamental frequency is going to stay the same.
Right,
Yeah, we are.
but it can have a little bit of,
Yeah, that's your audio on top of there. Let me put a tune circuit in here. Let me get this a little stronger.
okay, wow. I thought you only did it by making these taller or shorter. Shorter. But I guess not. I guess not.
So, let's do this. I think this is tune somewhere around
Okay.
So if I expand this out, I can see the carrier. There's your carrier.
Oh, so here's your carrier, okay.
And there's your audio on top of that.
That's on top of the carrier.
Yeah. Those carriers getting bigger and smaller.
Okay, okay, which one did you see the carrier?
So expand it out. The carrier frequency. So
That's the carrier frequency, okay. And then when we do that, we're looking at just maybe just this part right here.
Well, it's the average. Yeah. Those big modulated all the time. So if you just went to the middle there. 970 kilohertz.
I see. Oh, wow.
So if they stop talking, they'll just do a straight band.
And right there, you're going to what, a different frequency,
Yeah.
or you're going
Yeah,
to?
there's a couple strong stations too.
Okay. That's just the. That's the carrier. Okay. Wow. But it just changes the amplitude.
Yeah.
Okay. this right here is just pulling out this part right here.
Yeah.
What you're saying?
Yeah.
Okay.
Right, so we're seeing both sides.
Oh, we are seeing, right. Okay. Wow.
Now, the reason you need detectors, because it goes up and goes down at the same time, it's going to cancel everything out as far as the envelope. So you
Right.
drop off the bottom half, so then you can put it back
Yeah.
through the envelope.
Okay, that's nice. Oh, that's right, because
Yeah.
they're opposite, they're
Yeah.
180.
Yeah.
Yeah. Okay.
Let's see. I think we can.
Right, we are seeing both top and bottom. Just lop that off. Oh, okay, see, now that's starting to look a little more like
Yeah.
sound waves.
Yeah.
Okay.
So I've got a doubly balanced modulator here. We can place it in a, yeah, but I should be able to find out.
Clean AM.
This actually will generate two different frequencies.
Really? Oh, yeah, that's right. It's got two different channels.
So what we'll do is,
I mean, all these backwards guys.
okay. So 1 megahertz.
And, you know, audible sound frequency is what frequency?
About 20 to 20 kilohertz.
Oh, wow. Yeah, that's right. 20 kilohertz too, huh? Wow. You can really hear 20 hertz, huh?
That's your dog in here. It's exactly. Now, let's take a second one here.
We're using all this.
We're getting all of this.
But you know, sometimes just come back years later.
Well, that,
Oh,
What do we see? Huh. What's that?
that is a little bit of blow by there. You shouldn't be seeing anything.
Oh.
The second generator here. And let's see, channel 2. And,
Huh.
1,000 hertz there. Sine wave.
Oh, that's the second one there. So
Yeah.
I was looking up here.
Yeah.
Okay, how do you separate? Okay.
Modulation.
So we're at a megahertz and 1,000 hertz.
Yeah.
Okay.
So
Okay.
it's pretty strong. I'll just drop that down a little bit.
Okay. Interesting. Okay.
So that's, yeah.
Huh.
Now, let me, actually that double side in. We have a little bit of offset on both of these. There we go. There's perfect AM.
Really?
Yeah. So inside here is your carrier frequency. Inside here would
Okay.
expand it out.
Oh,
Also modulated. So
because that, okay.
That's beautiful. My little homemade, Bellus modulator works a lot better than their Okay, so what we have here, this envelope is audio.
It is audio.
Yeah. It's 20,000 hertz, and then the fuzz in between is the carrier. Expanded it out, you can see the carrier there.
Oh, that's the radio frequency, right, because it's in megahertz.
Yeah.
We can see
Yeah.
each one
Well, actually, that's,
changing amplitude.
this is actually your,
The audio.
no, this is a carrier frequency.
Oh, that is.
Yeah, yeah, no. If I reduce the audio to nothing, you can see. There's a carrier.
Whoa. Okay,
So
I
there's
see.
a
We're
carrier
looking at
frequency.
5.
So, it's on, and, okay.
1 megahertz. Okay. And just by changing the amplitude of that, eventually you've got the sound.
So if we went back here, you
Uh-huh.
see, there's a carrier, not much on it.
Okay.
And sound on here.
Ah. You're changing the lower frequency.
Yeah.
You're at
What? 1,000 hertz.
1,000 hertz. Yeah. Okay, that's your audio.
Now again, if I were just put a headset of headphones on there, the average audio is never change. You know?
Right, but you can hear a tone,
You
probably.
wouldn't even hear that.
Oh, you wouldn't.
No.
Oh,
So
because
that's
you have
why-
both.
Yeah, both. So you don't have any envelope left, so you would do is put it through a diode.
Okay. If we lock that off, and then you would get.
Yeah. Okay, so there's the audio. See, the whole top one way.
The top, oh, we're just got the bottom now. And then this is connected to,
Yeah, put modulator.
okay. And now you could hook up a speaker and you hear just a tone.
Yeah.
Of a sound that's at
That's
1.3 hertz. 1.3
hertz.
kilohertz. Oh, whatever that sounds like. Something like that.
Do that right here. Oh, that's loaded it down. That amplifier is too high, too low, and you can start loading it down.
Okay.
Oh, no.
Yeah, but we get the idea that that would be whatever that sound is.
Yeah, so if I change the frequency here.
So you change the frequency now to what?
Yeah, let's see, there's,
That 500 hertz? No.
there's
Oh, you did. Okay.
there's a 500 here.
500. Okay.
So we went back to the undetected version here.
Let me see what 500 hertz sound. Here's 500 hertz.
It's about 500 here. Yeah, there's 500.
But it's got both top and bottom, so,
Yeah.
so we wouldn't hear.
We would not hear that.
I'm assuming that'll sound relatively low,
Well, it's
because we can hear all the way up to 20,000.
440 is C above middle, A above middle C.
Oh, middle C,
Yeah.
440. That's that signal right there. Right? We're about 500?
Yeah.
Pretty cool, huh?
Triangle wave.
Now, what is that?
That's triangle wave.
Does that change the sound?
Oh, yeah.
Really? Wow. But it's the same frequency.
Yeah.
But a very different sound. Would it be more like, it sound very sharp?
So that's where, let's see.
That's normal. Okay. Wow. All the same frequency, just such a different sound.
Yeah.
Different quality of it. Wow.
So,
This one seems to have like a
that's the cleanest,
deep, the cleanest, but also like a deep part to it as well.
well, because you have only the fundamental, you don't have any harmonics, so,
Right.
if you want to.
Wow.
Fourier figured all this out too.
Oh, Fourier.
The French guy, so.
Wow.
So the sine wave is a fundamental for any repetitive oscillation.
Yeah.
No harmonics by definition.
Harmonic.
Harmonics are multiples of the frequency, so any distortion you have of a repetitive wave will always be harmonic distortion, which means addition or subtraction of harmonics.
Uh-huh.
A square wave is a fundamental wave plus every odd harmonic.
Okay.
So an odd harmonic is 3 times the frequency, 5 times frequency, 7 times frequency.
Oh,
So if we were to fill this in, and we have the third harmonic, we have like that, okay?
oh
We
wow.
have the same thing here. The more harmonics we have, the closer it's going to start filling in the corners and start looking more like a square wave.
Oh,
So if you take every possible harmonic there is, every possible odd multiple of the fundamental frequency,
yes.
and add it to there, it's going to be a square wave. If we take all the even harmonics, we end up with a triangle wave.
Really?
So you take a fundamental plus 2 times that, and times 4 times that, and then add them all together, and we'll end up with a triangle wave. And if you have an infinitely sharp pulse, like a radar pulse, well, it's not infinite, but a super sharp pulse, like this duty cycle here,
Right.
you end up with every possible frequency from DC to daylight. Not just the harmonic, but every frequency in
Wow.
existence.
Hmm.
So,
And what does that?
an infinitely thin pulse,
Right.
the short pulse. The entire radio spectrum with a very short pulse.
Does anything do that?
Well, radar comes close to it. Radar is very wide.
Radar. I see. Close. Does it?
But I'm glad that thing worked with both. I could do that.
Right?
Okay, beautiful waveform. So anyway, that's an actually pretty modern way of doing data modulation.
AM modulation, and this did what? Locked off the bottom half of this?
No, that did not lop up. It's only when you put the diode in here.
Oh, that was what did this do?
That actually modulates, that's what actually multiplies the carrier wave by the audio.
Oh,
That's what, how it actually generates that.
that's, okay. Oh, we wouldn't have heard of it had we just.
Would have done it, yeah.
Oh, okay.
See, if you just take,
Wow.
this is what makes modulation different than just adding. If I were to just take two frequencies and add them together,
Right.
it would only give us wouldn't give us much of anything, what we'd have. This is our carrier, okay,
Right.
and we just added this to it.
Sure.
All we'd have is a carrier which moves up and down,
Oh,
okay, but the amplitude would stay the same,
yes.
okay. So in order to get the amplitude to change in accordance with the input signal,
Yes.
we don't do the arithmetic addition, we do multiplication.
We do.
This little symbol is an actual mathematical multiplier. So we're actually multiplying one signal by the other. And the way we do it in this one, here we get this
Wow.
diode ring here, so that's actually a diode multiplier. So let's say it's simply at any point in time, it's the product of the carrier, our carrier amplitude and the modulating amplitude.
Product.
It's product.
And that's changing the amplitude.
That will change the amplitude, yeah.
I see. Okay. Is that a useful signal, the second orange line? Is that
No,
useful?
it's not.
It's not.
It's just going to look like a carrier. You're just shifting the carrier up and down, and
Right.
space doesn't recognize a DC potential.
Right.
If you could put a DC potential through space, it would mean something. But in space, if space only sees it doesn't see any reference level.
Wow.
So
Ooh. Okay.
pretty cool, huh?
I see. Mm-hmm.
Now,
Wow.
here's
Brain.
another subtlety which becomes very important as we start getting communications and worry about bandwidth and that kind of good stuff. And Fourier had this figured out too.
There's a lot of frequency pollution out there,
Yeah.
right? Well, I guess it does, what's the word, dissipate, or it does, what's the word we use?
I mean,
Over a distance.
over a distance it attenuates.
Attenuate, yeah.
Yeah.
Oh, okay.
But what's really amazing, you have all these infinite frequencies that don't interfere with each other,
Right.
In space, they
They don't.
they don't. Well, think of it this way, you've got a speaker there with one pair of wires, right? And you carry all those frequencies simultaneously,
Right.
That's what's called superposition theorem, which is extremely important in everything we're doing. Empty space is perfectly superpositional, which
Wow.
means there is no limit to how much power you can put into it. Now, I guess at some level,
And
some people have
information.
predicted you can actually burn space, but
Right.
it's,
How much power, how much information, how much it can take.
yeah, it doesn't, there's no limit to space itself, it's only the devices you have out there,
Wow. Okay.
Okay, so we talked about AM modulation, very important, because this is so fundamental to everything we're doing here. Now, a lot of your communications is FM, it's actually, in a lot of ways, a lot simpler, but to get the idea of what, first of all, I introduced you what amplification was, now we talk about modulation is what we're doing here. So we have to modulate something, and demodulation is simply putting information on a radio frequency carrier, and there's several things we can modulate. Here's a little thought experiment. You've got a single radio frequency carrier, okay, coming from some transmitter where you don't know anything about the transmitter itself.
Okay.
There's no modulation on it.
Okay.
What information do you have on that? If you had to find out everything you had about that transmitter, just looking at a single carrier, what could you tell about it?
Just looking at the signal.
Mm-hmm.
Um,
And the reason I say this, these are all things that you can modulate and put information on them if you wanted to.
oh,
So they're all characteristics of a signal that we could modulate.
frequency,
Okay.
which might tell you something about the dimensions of the antenna.
Okay.
Maybe.
Okay.
Kind of. Direction.
Direction. Good.
Can you figure out the distance?
Not easily, but
Not easily.
you can triangulate. Okay.
If you did triangulate, then you could figure out how much power this thing is putting.
Power. Yeah.
Right? How much?
Yeah.
What else? It's not modulated, it doesn't have information.
No, that's right. Well, my
Um,
point is, it actually does, whether you're intentional or not, there is information you can glean from it.
oh, there is, yeah, there is.
And you're done. So.
A direction, so there's more, we can figure out more, let's
Mhm.
see.
There's one more. I think that'll do it. I think there's one more piece of information we can figure out.
Oh, okay.
And we glanced at it earlier.
We did, we glanced.
It's crazy, it's going by fast. Polarization.
Polarization?
Yeah.
Tell me.
You have a horizontal and a vertical antenna that are cross-polarized. There's no transfer of energy between them. Cross-polarized.
Oh,
So as we rotate till we get the maximum signal, then
Wow.
we know what the polarization is.
polarization.
So you can modulate the polarization. It's not a real practical way of doing things, but there are some interesting things
Sure.
to do with that.
I know for my work, we have polarization,
Yeah,
because I have to twist the LNA.
Yeah, well, that's just setting it though. You're not
Yeah.
actually using it for modulation, but theoretically you could have like your mark on one polarization space on the other
wow,
experiment. So
polarization.
polarization, yeah.
Okay,
Yeah, radio signals are polarized, and unless they're
right.
matched up, you get no transfer of energy. Or you can get total attenuation by having
They have to be
perpendicular to
matched up, the antenna.
Now, it doesn't, they don't have to be perfectly matched up. As you decrease or increase the match, the bigger signal swing. But if they're exactly 90 degrees apart, you won't get any signal.
Well, that's pretty much what we use it for, because we double
Oh, that's right.
Yeah.
double utilize
Yeah.
Because the
frequencies.
wire-
So
oh, yeah.
we have,
Oh,
you have certain ones that have to be,
exactly.
Yeah.
we call them odd and even, but
Yeah.
certain this way, certain ones this way. So
Yeah.
if our dishes get moved or moved or anything, and you end up this way, then you end up
Yeah.
crossing into the other
Yeah.
one. So,
Because basically the antenna is just.
Well, we look at the direction of in order to induce a voltage in a wire, you have to have the electrons flowing in the direction of the wire.
Right.
Now, I guess if your wire's infinitely thin, you could
Right.
get some polarization across the cross-section of the wire, but that's
Right.
minuscule.
I see.
Now, there's another type of polarization with circular polarization, and every HF signal that goes into the ionosphere comes out circularly polarized. So you can put linear polarization and it goes through there. The magnetic field actually causes two counter-rotating signals to emerge from there. So
Wow.
that's really easy to see on an ionoson. So you actually get what's called the X and the O mode, one that follows an Earth's magnetic field, one that's perpendicular to it, and they have different polarizations. So that's a little more science geeky, but it's very real.
Next time.
Yeah.
But wow, okay.
Okay, now one thing we haven't talked about, and before I figured this one out too, is you cannot change the wave of any sine wave, or you cannot change the amplitude of any sine wave without changing the shape of it. Now that's kind of a what do you call it? No-brainer in some regards. I mean, you say, well, I'm not squashing it down.
Just the amplitude.
If the definition of a sine wave is that, and we've got something that's doing that, the amplitude's changed, but it's also changing the shape.
Shape,
The
okay.
shape.
But not the
Anytime-
frequency.
That's, the fundamental frequency, yeah, we live across it.
Right.
But what happens is you cannot change the shape, or you cannot change the amplitude without changing the shape. And anytime you change the shape of a sine wave, you end up with other frequency components.
Okay, see that again?
Anytime you change the shape of a sine wave, you end up creating other frequency components.
Sure.
And,
Which is what we just did. with-
well, that's the extreme case. Now, what we do here, if we want to analyze this, an oscilloscope has two axes, right? You're looking at horizontal, which is time, right? You got your time axis, you got your amplitude. Spectrum analyzer like that shows you amplitude versus frequency.
Oh, wow.
So if we were to plot this on a spectrum, radio spectrum, and here's an unmodulated carrier. Okay, we'll call this F sub 0. And this will be on your test, by the way, the SEC test. F sub 0, okay, 0 means your carrier frequency. F is frequency, okay? If we put modulation on it, on AM, and FM is completely different, but if we modulate out with a single carrier, and this is something that you can't see within the oscilloscope,
Oh,
you generate two other carriers. One's called your upper sideband,
wow.
and this is your lower sideband.
And they're equal but opposite time.
It's perfectly symmetrical.
Okay.
And these are separated by whatever your modulating frequencies is.
Mhm.
So if we put 1,000 hertz audio in here,
Right.
this is going to be your F0 plus 1,000
Minus 1,000.
and minus 1,000.
Sure.
Now,
Okay.
in AM, you put all this out there, and it's all mixed together, you know.
What are we measuring? What's the y-axis?
Oh, the y-axis is amplitude,
Okay.
or power. Now, I've got all the single sideband equipment here, which actually, you actually only use the sidebands, or you actually only use one of them. But for standard AM, you use the whole thing, okay? Because you need this to demodulate. You can't demodulate without a carrier in there. Now, in single sideband, you add the carrier in the receiver, and then you can demodulate it. But without that, you need all this information in order to demodulate it. So it's a fact that you're mixing these two products together, you're multiplying them together, run through the mathematics to do that, and it doesn't require high-level calculus, it's just some algebra. You can show that these two power levels have to be the same, and one's above carrier frequency, one's below. Now, in order
Again,
to...
is that what we saw here? That's essentially what we saw here? Or that's
No, we didn't. No, that's different. So you're only seeing amplitude versus time on that. You aren't seeing amplitude versus frequency of this.
Okay.
A spectrum analyzer can, but
So explain to me the differences the spectrum analyzer is looking at it.
well,
Based on
a spectrum analyzer, this horizontal axis is frequency,
Frequency.
and then oscilloscope is time.
Right, yeah.
Sure. Okay. It's going to look the same. It's just different
Yeah.
information.
Right,
So
yeah.
I'm going to have to think about that. Okay.
So we have these three signals there, and when you either modulate or demodulate them, you need them all together. Now, in order to transmit this, your whatever transmitter he has to be able to accommodate all of that. That's your total occupied bandwidth. Okay?
Whatever you're okay.
So if you're transmitting 10 kilohertz audio, you're going to have sidebands up at 10 kilohertz, okay? So you have to be able to accommodate twice that.
Up and down 10 kilohertz.
Your
Yeah.
bandwidth has to be 20 kilohertz wide to be able to accommodate that.
Right.
And let's see. Well, of course, we aren't sending single tones there in audio. We're finishing everything across. So we got all these sidebands, pairs of sidebands,
Wow.
scooting in and out all the time. So,
So you need antenna that are
well, you need your whole transmission facility has to be able to accommodate.
Okay. And what part of that is on the test?
All of it.
The fact that there's a
In fact, there's the sidebands, you have to, the relationship of the sidebands, how they respond to modulation, how to demodulate the AM.
and how to demodulate.
Yeah.
Okay, have to read up on that. Yeah.
And this is why you can't have an infinite number of broadcast stations or any kind of station on with finite spectrum available, right?
Right, it just gets so cluttered so quickly.
Yeah.
And why else can't you have an infinite number of stations? Because
Well, because if they're all overlapping the same coverage area, you know, you can't stack them next to each other, you know, so you have to be able to separate them.
Yeah.
Now,
What's the standard of separation?
well, for AM broadcasting in the U.S. it's 10 kilohertz between carriers. So there actually a little bit of overlap, but not in the same market, but you may overlap a distant station there.
10 kilohertz, okay,
Now,
that's pretty good.
cell phones all do occupy the same frequency range, but they do it by code division multiplexing. So they're actually interlacing themselves there, so they aren't on the same frequency at the same time, you know, so they
Really?
synchronize there, so There's a frequency division multiplier where you simply do it by slots. There's also what's called spread spectrum, where they kind of randomize where the frequency is within range there. And it's only if you have the decoding to de-randomize it that you get the signal there. So they actually do overlap frequencies on cell phones. So.
Okay. And is that because you can do that easier at higher frequencies?
Well, it's possible at higher frequencies, not easier. I mean, that kind of stuff you can't even do. You come close to imagining on lower frequencies.
I see.
But very broadband signals there. So.
Right.
You got a cell phone with you?
Sure.
Fire up the spectrum and we'll take a look at that. Let's see, that's not 4G, is it? You have an old?
That's 5G.
Oh, that's even 4G.
This one might be 4G. Why, you want 4G or 5G?
4G, I don't, 5G is up at 5 gigs, I think I'm going to.
Pretty sure this is 4G. Pretty sure. We'll see. Oh, and yours doesn't go to 5.
Yeah.
Really?
We'll see if I can see it. Okay, just dial up a number like that. Might be 30 here.
Should I put it up close to you?
No, that should make any difference.
No.
Down to 60. Oh, there you are.
Really?
Well, I'm not going to start there. Okay, yeah, I think it's going to be good.
Maybe that was it?
No, that's a spur there. It's going to be way up here someplace.
Is it? Okay.
Yeah.
Well, let's say I was talking to somebody.
What you get is, if the, well, actually, it's spread spectrum from the beginning, so you'll never see just a single carrier. You'll see that it's already frequency modulated by pulse code modulation,
Wow.
so already a wide signal out of the transfer.
And these decode that. And
Well, this doesn't decode, it's just.
that does it, but it just
Yeah.
detects it.
Yeah.
So you would just see the wide kind of. Wow. Mm-hmm. And this is frequency and amplitude? Oh, okay. Which is different than that, which was amplitude over time.
That's
Amplitude
it.
over time. And this is frequency. Amplitude over. Okay. You got the batteries? You want me to turn on the battery in the car? Start blasting?
Oh, there we go.
And turn on the radio in the car? Oh, there you go. Nice. Ooh, there you go. Yep. Oh, okay. Was that a little bit of a wideband too, or you see
No,
one spike?
Let's see.
That's you?
KL7AJ. Let's see.
Wow. Was it mostly like electrical engineers that are learning this, or who's learning this?
Who's running one?
Learning this field right now. Who's learning this? Well, a lot of people.
Here's the weather service right here.
That's the weather service. Okay.
And this up here is, that's like your police and fire frequencies.
Oh, okay. Oh, yeah. There's a lot going on there.
There's nothing broadcasting.
Well, I guess you guys are learning this quite a bit. You know.
We use spectrum analysis.
Yeah, here's the FM broadcasting here.
was it mostly engineers that are kind of creating and maintaining, is it electrical engineers or what?
Well, RF techs, you know.
RF techs. Okay. I mean, and this is stuff you learn after college. Are there courses in college you're teaching?
Well,
In engineering somewhere?
yeah, you have to actually specify, you know,
Uh-huh.
you just say, hey, you know, you just take the standard EE courses, a
Right.
bunch on digital stuff, so.
Right. So this might be like the master's level where you're getting into.
Well, it's just a kind of a side thing.
It's a
You
side-
know,
okay.
It used to be electrical engineering by definition was radio.
You're right, and now it's an elective
Yeah.
of electrical, okay. Wow, but I mean, an elective is so much different than, hey, let's really dive into this, and really, which is what it used to do.
That's what it used to be. Well, there's the AM broadcast down there.
Wow, so there's maybe a lot of knowledge being lost, or kind of,
Well,
or not as many people know.
Yeah, it's,
Okay. Well, I'm just curious, you know, how do you keep this information going?
kind of like what I'm doing here.
That's exactly,
You know.
it is. Wow.
So anyway, the night is not over.
The night is young.
The night is young.
Our friends are Friday.